started. Now we are recording. Let's get the slide set up from current slide. Okay. Now, before we get going on this, let me go over just a few things. Number one, we did finish chapter 16 last time, and I thought we would just get started on the lab, but of course, okay. Everybody's got a copy of the lab now, right? If you read through that, you'll find out the first big chunk of that is, I think, called Procedures Part A or something like that, is on observations of the moon. Now, you have to pick the time you want to do it. You have to pick the place you want to observe from. Depending on what time it is, the moon may not be out. Like if I were choosing 10 o'clock at night, which would be about the time I would choose, right now I don't think it's out there. Last night it wasn't, so I doubt if it is today. But you'll need to listen to that lab, and that lab will explain everything you need to do and the things to check. If you have any questions, ask them on Tuesday. All right, so we finished that one. And then we did the other part of the lab, which is the bulk of the lab we did in class, but you can listen to the YouTube video, and I think you'll be able to hear everything done. If not, get with a friend or something, okay? Now, the test will be the last 30 minutes today. That's Chapter 16 test. There are a few people who are planning, have already taken tests, they're behind in, and some others have spoken with you about it today. So you can take them in whatever order you want. Last 30 minutes today will be the test on Chapter 16. The next thing up is our visit to the planetarium. But like I said, I called Mr. Weigel at least twice yesterday, couldn't get him. I emailed Mr. Weigel and haven't gotten a response yet. So I don't know. I don't know if he's on vacation or if he's so swamped he doesn't see it. This is Darius, right? Yeah. Okay, and that's what you go for, right? Yeah. You got the circuit. Okay. And I bet you didn't get a copy of the last lab, did you? No. Okay. While I'm standing here, yeah, we did it last time. And you'll need to listen to the YouTube video to find the directions. But it's not out there yet. I've got to get it on the playlist, and that's probably going to be tomorrow morning. Okay. Maybe today, maybe this afternoon. I'm going to try to do it this afternoon. If I have time, I will. Okay. All right. So the next thing is that, and since I don't know the answer, I'm guessing it won't be Tuesday, okay? But if I find out over the weekend or Monday that he says, yes, Tuesday is the only day I can handle you, then I will put something out there on Blackboard, announcement and stuff. How long a time do you need to make arrangements?
I can, as long as I know a day in advance.
A day in advance. So Monday, I've got to get that message on Blackboard by Monday, right?
Yeah. As long as
Are you here on Mondays?
I'm at home. So
At home on Monday. Okay. Can you check email messages and stuff?
Yeah.
Okay. Well, check on Monday and see. Yeah. Unfortunately, Monday I'm in class from 8 until 11:10, and then again from 12 until 3:15. Yeah.
As far as, his note taker, will
Yeah.
you need me there to take notes, or is it just a fun field trip?
This is a field trip. You don't have to unless you just want to go see the planetarium too. You're welcome to. He doesn't. Yeah, we don't mind. Okay. But no, there's no notes. You're not going to be tested on the field trip. It's just it's a neat thing to see and to experience. So you're welcome to come if you'd like, but there's no requirement for that. Okay. All right. So we start today on Chapter 17, which is also starting the section on what I would call geology. It's rocks and minerals, plate tectonics, and that type of thing. So we got several chapters on this. I think 4 or 5 chapters on this. Then we do weather, and then we do oceans, the Earth's waters. So that's pretty much going to do it. All right. Any questions before we get started on this? And here we have Shelby. All right. Now, any of you who were here last time, did you try to get something set up for your moon observations?
It was cloudy last night.
Yeah, that's what I was thinking. I didn't see the moon. I don't, depending on what time you were out there, I don't know that it was even up yet. Yeah. What did you say?
It was raining where I live.
Yeah.
so I can-
And it rained some last night too, so not the best of conditions, but as far as I know, the moon wasn't even visible at 10 o'clock. I didn't see it when I put the dog out. I usually look for it. Okay, any other questions before we get going? Okay. Chapter 17, we're starting with rocks and minerals. I guess I ought to get my book over here too. Now, I hate to be sitting down, but to be close to the computer, that's what I'll do. But I'll be up and down. Okay, rocks and minerals, chapter 17, beginning of sort of the geology or earth science part of the class. Core concept here, and again in the book, why they put white on yellow background, which is really hard to read. This is a lot easier to read. Earth is a dynamic system, a body that cycles rocks and minerals through ongoing changes. Okay? Now, if you haven't noticed it, just about everything in nature cycles. The old saying, or the common saying, what goes around comes around, that's really true in nature. Everything that's happening now has happened before and will happen again, pretty much. So Earth is a dynamic body, always changing, but always repeating too, okay? Cycles rock, that means what is a rock today may have been a different rock sometime in the past, and probably will be something different sometime in the future. But ultimately, they come back around. Now, we're talking about rocks and minerals. However, the order that we do this is going to be minerals and then rocks. So we'll come back to the rocks later. But this is going. This is a picture, and we'll talk about this later. This is one of the oldest rocks they have found. This is I don't think my book has this particular figure here. It's somewhere else. But we'll come back and be mentioning this before. This is a metamorphic rock. It used to be a sedimentary rock, and you can tell what was flat level sediments have really gone through a lot of distortion over time, over huge amounts of time. And not only distortion, they have actually changed their crystal structure because of heat and pressure. We'll come back to that in the last half in the rocks part. We're going to do minerals first. Okay? So let's get started on minerals. Now, actually, before we jump into minerals, let's look at the earth, the solid earth materials. Okay? Now, of course, what's most of the surface of the earth made of? Second? Okay. Surface of the globe. What's it covered with? Most of it's water. More than 2/3 of it's water. In fact, it's probably even a larger percentage of that. But underneath the water is rock. Okay? So you're right, it is covered with rock, but we're going to focus on the solid earth materials. Last chapter we'll do the liquid part, the water part. Okay? Now, what are some of the characteristics of these solid earth materials? They're not uniformly distributed. Birmingham, Bessemer area here, higher in iron than most areas. Okay? Pittsburgh area, probably a little bit higher than us, or about the same. And in the U.S., there are probably few areas that have as much iron near the surface as we do, or did anyway. Okay? But other areas may be richer in other things. Underneath us is mostly, and we'll talk about this later, but one blank on the thing. It's a sedimentary rock. It's calcium carbonate is the chemical in it, but it's limestone. Okay, limestone. Whereas go over to Georgia, and most underneath Georgia is granite. Okay, and yet we're right next to each other. So it's a very non-uniform distribution of the materials, solid earth materials. Now, not only is it not evenly distributed on the surface, it's not evenly distributed up and down. Okay? In fact, when we were talking about what is on the surface, and people said rock, and then we said water, but yeah, a lot of rock even underneath the water. But if you go deep enough, it's liquid again. But now it's not liquid water, it's a molten or melted core. Okay? Now if you think about this, and we've mentioned it before, when star formation or whatever other activities are going on, you have gravitational pressure. All the weight of everything above is pushing in, being pulled in by gravity, and in the center where there's molecular motion going on, that pressure makes a lot of heat. And that's hot enough to melt the strongest, most, whatever metals are in there, they're melted. So now, we'll talk about this a little bit later, but actually the innermost part of the molten core is solid again. Just because there's so much pressure there, it's forced it back into a solid lattice. Even though it's hot enough, it should be melted, but the pressure moves it back into a solid again. So it's not uniformly distributed. That molten core contains mostly heavy elements. Basically iron, nickel, and things heavier than that. So who knows? There's probably a lot of gold down there, and silver, and platinum, uranium. There's probably all sorts of very valuable stuff in our core. No way to get to it. And if we got to it, we'd be toast. No way to deal with it. Most of the heavy elements are down there. It's only rarely that a lot of that stuff comes near the surface, but when it does, pretty valuable. Actually, the continent of Africa actually probably has some of the richest minerals. The nation of Congo, Democratic Republic of Congo, used to be called Zaire. Before that, they were Congo. That is probably one place that more very rich, very valuable minerals exist, and yet they're one of the poorest countries on the planet because they have been exploited so badly by other countries. So it's a sad, sad story there. Okay, where we live is on the very crust. And this, by the way, is a very thin crust. Okay? Thin surface crust. Mostly the lighter elements. Iron and lighter than iron. Okay? Silicon, carbon, oxygen, all those things. 8 elements, just 8 out of the 90-some or 100-some odd elements we know about make up 98.6% of the crust. The next figure will show that. In fact, I guess I better go and get that up. Okay? So, here is the Earth's crust, the breakdown of the Earth's crust. Okay, now, we say what covers the surface? It's mostly water, but there's always the solids. But what we didn't talk about, there's also an atmosphere all around us. It's gases, right? Okay? It's a thick atmosphere, too. Not as thick as Venus, but it's a pretty significant atmosphere. Thank you very much for being there, because that's why we don't get fried to a crisp by the dangerous radiation that the sun puts off. And it happens to be an atmosphere that protects us just right. Okay? Now, that atmosphere is made up of gases, like I said. This is not talking about oxygen in the atmosphere. This oxygen you see in the crust is actually part of the solid matter. Can oxygen ever be solid? Before you answer that, let me get Emmanuel here. Okay. Looks like we're missing Coco still, Carl still, Brittany, and Terry. Okay. So everybody else, we got them coming in. That's good. All right. Can oxygen ever be solid? I think I just mentioned what we are underlain by is a mineral called limestone. made up mostly, and I gave the chemical name before I could think of limestone, crazy me, calcium carbonate. You know what carbonate means? Carbon with the ATE means oxygen. CaCO3. Okay? Now calcium has an atomic mass. You've got one of the big books, you can see this in the very back of calcium is, if I had any light here, it's 40. Carbon, 12. Oxygen, 16. But there's 3 oxygens. 3 times 16, 48. Most of the weight, the mass of that piece of limestone is oxygen. But it's oxygen and chemically bound into a lattice, crystal lattice, that makes up calcium carbonate limestone. Okay? So that's why the biggest element, almost half of the solid earth crust, okay? This isn't deeper, but solid earth crust, almost half of it is oxygen. A gas, but it's in a chemical composition that is a solid. Okay? Surprising but true. Next, after almost half of it being oxygen, more than a quarter of it is silicon. Okay? Silicon is the element just below carbon in the periodic table. And what mineral or what do we run into a lot that is largely silicon? Anyone think of anything? Any of you ever been to the beach? Sand. Most of that pure white sand. Now sand really is a particle size distribution. It's not an actual mineral. But most of what we call sand, that whitish to clearest little crystals that get in your shoe and hurt your feet, you know, that kind of stuff, that's mostly made up of silicon dioxide. Okay? There's oxygen all over in it too. Okay? And you almost twice as much, there's twice as many atoms of oxygen, but the silicon is a heavier atom, so probably more than a third of the mass or weight is oxygen. So silicon dioxide. So silicon on the surface is what we think of the solids, the first one. There's oxygen, those in solid form too. After that we have aluminum. Aluminum is a fairly common, but it's not aluminum ore. You can't just say, oh, let's mine some aluminum here. That happens a lot more rarely. Where aluminum occurs is in other minerals. For instance, your clay minerals. Clay minerals typically have 1 to 2 layers of silicates and another layer of aluminates. Okay? So, on your clays, I don't want to say a third, but a large portion of that. And the minerals that those clays came from generally contain a lot of aluminum. So this isn't aluminum that you can go out and mine. It's all tied up just like the oxygen is in other kinds. Iron is near the surface, and we've got probably more than most, about 5%. Calcium, as I said, calcium carbonate, calcium sulfate. There's a lot of calcium compounds that do make up the surface of the or exist on the surface of the earth. There are quite a few sodiums. You won't find elemental sodium. Sodium is far too reactive for that. If you found it, you'd probably be burned because it's going to react immediately, burn you like crazy, because anytime it gets close to water, it explodes basically. So yeah, you don't want to handle sodium, but sodium exists in sodium chloride, that's salt, sodium nitrate. Sodium is all over and everything, but still not huge. Potassium right behind sodium. In fact, those two, it's sort of like Uranus and Neptune. They do lots of things together. In your blood, sodium and potassium are the things that, and not just blood, in your nervous system, those are have y'all heard of sea salt used for, salt we use for food? Sea salt is potassium chloride and sodium chloride. Same combination you have in your blood, potassium chloride and sodium chloride. Same type of ratio you have in your neural system. That's what sends all of your electrical impulses. Your vision, your hearing, your thinking, your muscle movement, everything that you do is because of a balance between sodium and potassium ions, and that's what sends the signals. So yeah, they're all over here. But it's a common mineral in the surface. And then magnesium, shortly after, just a little bit less than sodium. Magnesium and calcium seem to be similar, but they're further apart in the surface, in the crust, and then everything else. So these are the 8 elements: oxygen, silicon, aluminum, iron, calcium, sodium, potassium, magnesium, make up 98.6%. Only 1.4% is left over as all the other elements. There's your gold, there's your silver. I mean, everything else is 1.4% of the crust. Okay? Now, if you go deeper into the earth, the entire earth, that counts the core, the mantle, everything else, look at how this changes. No longer is oxygen number 1, but iron down here that was number 4 before, it's number 1. Big time. 33%. A third of the whole earth is made up of iron. Is that iron we can mine? No, it's way too deep, way inaccessible. But because all this is on the surface, and there's some further down, oxygen is still number 2 at almost 30%. A little less than a third. Silicon, because all this was on the surface, it gets squeezed some, but there's others lower down to 15%, about half of what it was before. Okay? Look at who goes the big winner here. Besides iron, magnesium moved from number 8 to number 4. 13.9%. Fully 3 times or more increase. Nickel wasn't even shown up here. It was in that other 1.4%. It's moved up to 2% here. Calcium has dropped from 3.6 to 1.8. There's still calcium down deep, but a lot of it was on the surface. Aluminum has dropped big time. It was 8.1%. It's now 1.5% of the whole earth. Sodium has really dropped pretty much too, 2.8 to 0.2. In fact, I would say probably most of that sodium in the whole earth was, not most, but a fair amount of it was in the crust only. And potassium, that's off scale. It's now in the others of 1.9%. Okay. Okay. So, 8 elements make up all but 1.4% of the Earth's crust. Now, rocks and minerals make up the solid crust materials, and that's what we're talking about here. So rocks and minerals are going to have large amounts of oxygen, silicon, aluminum, iron, certain amount of calcium and sodium, potassium, and magnesium. Deeper, you get more of some of these and less of the others. The lighter ones are mostly on the surface. The heavier ones are deeper, as in iron. Magnesium really isn't that heavy, but it still exists down low. I don't know exactly why. Nickel, those are more at in the interior. Okay, near the core. Okay. So, as we said, the name of the chapter was Rocks and Minerals, but the order we do it after that introduction are minerals and then rocks. Okay, so what do we mean by a mineral? Here is a classic definition, Earth science definition of a mineral. A naturally occurring, one big key feature, inorganic, another key feature, solid, and then it says element or compound. Mostly compounds, but some are elements, with a crystalline structure. Okay? Now that almost ties in with being solid, but not completely. Okay? So there are 4 big elements there. Naturally occurring, inorganic, solid, crystal. Okay? Now, what's the antithesis of that? Cannot be synthetic. That wouldn't be naturally occurring. Okay? So in other words, The metal used in this chair right here is synthetic. That's a solid. Now, the ore that produced the metal, that was naturally occurring. That would have been a mineral. This chair is not exactly a mineral anymore because it's been synthetically produced. Okay? There's many other examples. I'll just stop at that. Not produced directly by a living organism. That's what it means inorganic. Organic means coming from living organism. Okay? So the fatty tissue, we won't talk about that. That's not a mineral. Okay? That is produced by me. My bone is not a mineral. Okay? Now there are mineral components of it, but it's not a mineral itself. Now, some of those dinosaur bones, they may actually not be dinosaur bones anymore. It may be that naturally occurring minerals have replaced the calcium in those, and they made fossils. So if it's been fossilized, it now may be a mineral. But before it was a fossil, it wasn't. Okay? So, not directly produced by a living organism. Now let's get back to that calcium carbonate, limestone. Guess what? Originally, that probably, not totally, but parts of that could have been made of shells and bone fragments and other things that were deposited. But over time, that's changed its chemical structure, changed enough of its characteristics, now it's become a mineral. It didn't start off that, but that's why it says not directly produced by a living organism. So the bone would not be, but the calcium that leached out of your bones and reformed into calcium carbonate, which made limestone, that now is a mineral. Because it wasn't directly produced by a living organism, but somewhere generations back it may have been a living organism. For instance, any of you have a mineral on your ring? As in diamond? Okay? Would you say that's a mineral or not? So, yeah, most of the time that is a mineral. However, there is a lab at UAB, a group of physicists there are studying synthetic diamond. They are producing that. They're taking coal and putting out a lot of heat, a lot of pressure, and producing diamonds. Not very big diamonds, not very valuable diamonds, but diamond. But that's been synthetically produced. Okay? But those diamonds that they mined in the ground, that originally was coal. Coal came from organic material, generally. And is that, but yeah, by this time, it's changed enough that it's become a mineral. Okay? Not directly from a living organism. And must have a regular repeating pattern. Now again, we're talking about minerals. There are certain, one reason I forgot, we got some in the room, but it's not as obvious. What would you say about this? Glass. Say again? Mineral? Okay? Not quite. And here's why. Number one, it came from a mineral, because where does glass come from? Sand, that silicon dioxide. That's where they get it. That's the composition of that glass, the silicon dioxide. However, you have melted that mineral, silica, melted it, done other things to it, blown it, and you have, number one, synthesized it to make glass. But number two, it sounds strange, but it's true. In one technical definition, that glass is not a solid. Looks like a solid, it feels like a solid, but it really isn't. The reason it's not, it's not a solid crystal, let me put it that way. It doesn't have a crystalline structure, and it goes back to how that glass was synthesized. It was cooled quickly. If it had been allowed to cool slowly, which may have taken naturally maybe even years or something like that, then that would have been formed back into a crystal structure. But when it cools very rapidly, the crystals don't have time to get in place. Because you see, a crystalline structure has to have a very distinct, regular, repeating pattern. The glass doesn't have it. It formed too quickly, it was cooled too quickly, and it doesn't. There are actually some rocks out there that are naturally occurring, inorganic, solid elements, or compounds, mostly compounds, but they don't have crystal structure. Technically, they're not minerals, though we sort of treat them like they are. Can anyone think where they would be coming from? What kind of rock is cooled very quickly? Second? Second? Okay, igneous rock did come from melted stuff, but most igneous rock is crystalline. It cools slowly, believe it or not. Some cools faster than others. We'll talk about that. Second? I'm too far away to hear. Okay, sedimentary, that's a kind of rock. They're not minerals, but they're made up of minerals. Okay? My key is it's cooling quickly. Where do we see most of the molten rock? Volcanoes, exactly. If the volcanic material cools very quickly, which in air and certainly in water is going to cool quickly. If that happens, that may not form crystalline structures. It may not have that regular repeating pattern. And what they actually call that is volcanic glass. Abyssinian or something like that. Yeah. Is that? Are you a what is that? Game of Thrones fan? I think that shows up in that. I know it was in the books. I haven't seen the show.
Yeah, it does.
Yeah. It was a sword that's made out of that. It's supposed to be able to kill the whites or whatever they are.
Yeah.
Okay. But that's science. That's fiction. That's not even science fiction. That's just fiction. But it is an actual mineral. But it's a glass. It's not actually a crystal. Okay? Now, one thing that is a crystal, now, I'm not saying all this is mineral, but actually it is. Sodium chloride. Actually, the crystal name is, the mineral name is halite. Okay? I'll tell you sort of where that comes from. In your periodic table, which if you have the little thin books, you don't have one because it's in a different chapter. And I thought they were going to put this on the outside cover, but they didn't. The first, the seventh column over here. Now it looks like more than 7 columns. The early 7 basic columns. 1, 2, 3, 4, 5, 6, 7, and then 8. That 7th column there is called the halogens. And chlorine belongs to the halogens, so they call this halite. Why didn't they use sodium or something else? They just call it halite. That's the name of it. A halite crystal is a very regular pattern of sodium, chlorine, sodium, chlorine. No 2 sodiums are ever next to each other. No 2 chlorides are ever next to each other. They're always a chloride. It's always associated with all sodiums around it. Every sodium has all chlorines around it. Okay? Sodium chloride. It's a cubic structure. These make little cubes here. And there's one thing wrong about this visual illustration here. It's correct in your book, or in my book anyway, wrong on the slide. Can anyone see it? Notice I said no 2 sodiums, which are the yellows. No sodium is connected to any other sodium, only the chlorines, but chlorines are only connected to sodiums. Chlorines are the blues. Right there.
Yeah.
That's a blue, that should be a yellow. In your book, it's a yellow. In here, they did it wrong and made it blue. This has a chlorine touching a chlorine, or connected or bound to a chlorine. Doesn't happen, okay? That was a sodium, okay? Should be yellow. Now, what's that? I'm sorry.
I said they did it right.
Yeah.
So the blue dot is on the
It's
other
yellow
side.
in your book, right?
Yes.
Oh, you don't have
It's
it.
on the other side of it. They put it blue on the other side. They're putting it on that far end on the corner. That's
Yeah.
where that blue dot going to.
Yeah, but you see, this is showing one complete block here. The others are not showing the interior ones, but that should be a yellow. Should be a, because you see it's, technically it's touching that blue, this blue, and this blue. Yeah, that's a yellow touching that blue, and that blue. This blue should be touching this yellow, yellow, and that should be yellow. This one should be yellow, yellow, and that should be a yellow. So that should be a sodium. Now, let's just time out for a second here. Let's think about sodium chloride. I think I've already mentioned sodium is a very soft metal. So soft you wouldn't even think of it as being a metal, but it is classified a metal. Very, very, very reactive. In fact, anything in that first column, which are called the alkaline metals, those are very, very reactive things. They usually don't exist by themselves. Sodium, you will not run across a piece of sodium if you're digging in the ground. You will not find that. Okay? When I say it's very reactive, it is so reactive that if, chemical labs, like if you were taking a chemistry course, they had a lab and had the elements back here in somewhere, it would have to be stored in a jar under oil. You could not let it be exposed to air, because all air has some moisture in it. If a piece of sodium were to touch any moisture at all, it's going to explode big time, okay? Because it's so reactive with water. So they have to store it under oil. That's why you can't touch it. There's enough moisture in your cells, it would immediately burn your cell. Blister them, because it's trying to pull that moisture out. And it would be a very hot reaction at the same time. So here we have an explosive metal, sodium, combined with chlorine. Can anyone tell me anything about chlorine? It's what?
Flammable.
I guess it is, yeah, because you can have chlorates, which obviously have combined with oxygen, but the major feature of it is what? Highly poisonous. It's a green gas that is extraordinarily poisonous. Okay, and you would not want to get around it. There are tanks of chlorine that they send on trains and sometimes on trucks and stuff, and they have all sorts of warnings on them. If that train derails, they're going to have hazmat teams all around those chlorine tanks. And if any comes out, people are evacuated. It's a dangerous, poisonous gas. So here you have a yellow, soft, explosive metal that combines with a green, poisonous gas. And what does it form? Table salt that we put on our food and eat, and it doesn't bother us at all. That shows the power of chemical reactions. The chemical bonds change everything. They change the nature, the characteristics, and everything of both of the elements going into it. It's a clear crystal, or whitish clearest crystal that we use to season food, okay? Made out of a yellow explosive metal, soft metal, and a green poisonous gas. You combine them together, it forms a very regular pattern. And if you do have a very strong magnifying glass or a microscope or something like that, put some salt crystals down there. You'll see the actual crystals themselves are very cubic in nature. Little cubes, okay? Very little cubes, where they are. So there is an example of a mineral, halite. Now, will the salt that you shake out of your shaker be halite? Probably not. It's all, well, it may be formed from halite, but they have purified it and recrystallized it and stuff, so it was synthesized. However, if you do use sea salt, okay, My wife got some from some store somewhere recently that it actually pinkish kind of crystals that you almost have to grind to use them, because that may be actual sea salt. And that's not just sodium chloride, it's sodium and potassium chloride. That may actually be a mineral. So let's look at this crystal structures we were just talking about. Crystals can be made up of one or more kinds of elements. For instance, diamond is pure carbon. Pure carbon. Now, where do we see most of our carbon? Do you have any pure carbon in a second? Anywhere in your house? Second? Pure carbon. Yeah, somewhere around your house. Any of you have a fireplace? Soot? That's pure carbon. Is that a lot like diamond? Chemically, it's identical to diamond. Crystal structure, you can't be more different. Okay? Yeah. So diamond is a pure carbon, but it's a three-dimensional crystal that was formed under enormous amount of pressure and very high temperatures to form that, to force those carbon atoms into the crystal structure that makes diamond. Can anyone think of some characteristics of diamond?
It's hard.
Hard! It is the hardest, at least naturally occurring substance that I know of. There may be some synthetic things, I don't know, but I think diamond is still the hardest. Yeah.
You can cut just about anything.
Is what?
You can cut just about anything.
Yes, it will cut anything. It is harder than anything else. It cuts glass, it cuts rock, it cuts anything. In fact, talking about synthetic diamonds, I don't know if these were or not, but we had when we bought our current house, some previous owner had poured a concrete slab all across the back part of the property, must have been 70 feet or more, and probably a good 20 to 25 feet this way, around a walnut tree, a pecan tree, several other not so nicer trees, but trees, and it was thick. It had reinforcing rods in it, and we said, why? What is that doing back here? What? And someone said, the realtor said, we don't know, we haven't talked with him about it, haven't asked him that. He said, however, one of the neighbors said he thought they put it there so that the kids could play on the swing set and not get dirty. I said, oh yeah, you'd much rather having broken bones than having dirty pants, you know. Yeah, you know, I couldn't imagine having kids play on, and it was not smooth concrete, it was rough. I mean, miserable, I don't know. Anyway, we wanted that broken up. Now, I wanted a little bit of it left because I wanted to put a shed there. The shed that was on the back of the garage when we bought the property was just rotting and falling apart. It was actually dangerous to be in, leaking, so it wasn't doing the function of the shed, and it was uneven floor. It was just a mess, and we tore it down. But I needed a shed to put the lawnmower in and that kind of stuff. So here's a concrete slab, let's use it, you know. So the end of it I wanted to keep, but the rest of it I wanted broken up. So we hired a contractor with a company called Reliable Rentals, and they had bobcats and other things they rented out. So they came out with a big old bobcat with a hammer drill on the back of it and broke it up. I said, just shoot for 1 foot square. I know it's not going to be 1 square foot, but you know, shoot for that size. I don't want it any smaller or any bigger than that. I want to be able to handle it, but I want to be able to use it if I needed to. And they did a pretty good job on it. Of course, it didn't all break that way, but a lot did. But I said, I need this in. So they came in and brought a huge, you know, operate like this, circular saw, I mean, on wheels, you know, and it had diamond blades on it. And that diamond blade cut right through that concrete, right through the reinforcing rods, the rebar that was in it, right through the rocks, whatever was there, cut right through because it was diamond. That had been just a metal blade. Now it was metal, but it was coated with diamonds. So the diamonds provide, and diamonds are abrasive. That's the key. They're so hard and nothing will break it. They are very, very, very abrasive. Okay? Now, that soot that you have in your fireplace, a variant of that probably cooled too quickly to really be a crystal, but there is another form of pure carbon that some of you may have used, and I know all of you have used partially. Does anyone know what's in this pencil?
Oh, well.
Graphite. Graphite is a black, solid, but a very smooth thing. In fact, pure graphite isn't hard enough to be in a pencil. What they do is mix graphite with a clay, kaolinite, and that makes your pencil lead. If it's got a lot of kaolinite in it, it's going to be a very hard lead. Softer leads have more graphite, less kaolin. But it's very slick. It goes right over the page. Pure graphite, they actually use as a lubricant. It is that slick. It's pure carbon. Just like diamond is pure carbon. Diamond is a beautiful clear crystal, and graphite is a black, slick lubricant. How can that both be carbon? The crystal structure is different. The crystal structure of graphite is a two-dimensional crystal that slides past each other really easily, and that's what makes it a great lubricant. Whereas diamond was formed under much more higher temperatures, much more pressure, and became a really strong three-dimensional crystal that you can't break those bonds at all, and that's what made it an abrasive. Question?
Yeah, why is it called pencil lead if it's not actually?
It's not lead. I don't know why they name it that, but they call it pencil lead. It has hopefully absolutely no lead in it, because people are always licking their pencil, or some people do, and you don't want to be licking lead, but it's graphite and kaolinite. Okay? Now, quartz, on the other hand, is a crystal that is made up of two elements, silicon and oxygen. They call it silicon dioxide, or sometimes just silica. Silicon and oxygen. Two-dimensional structure. Now, it's also a clear crystal. In some ways, it looks a little like a diamond, not nearly as sparkly, okay, not nearly as valuable, but it is a crystal structure, not unlike a diamond. But it's made up of two or more very common elements. Now, how do we classify these crystal structures? This is based on the surface symmetries. Now, this is really tedious, so don't sweat this. I'm not going to test you on these structure symmetries, but I do think it's nice to know these things so you can at least recognize the words. Six major systems: isometric systems, hexagonal, tetragonal, orthorhombic, monoclinic, and triclinic. And I'm not going to go into the differences in all these, or even what makes them this. I'll just give you some of the basics. Okay, isometric. Does anyone know what the prefix iso means? Say again? No, actually that would be uno. Okay, iso would be same. Have you ever heard of an isobar? On a map, that's a line of equal pressure, barometric pressure bar. Isocline, that would be a topographic map where everything is listed by equal altitudes. In other words, showing mountains that they get smaller, or depressions, or ranges, they read like this. So yeah, iso means same. An isosceles triangle is a triangle with two sides the same. Okay? Like Terry. Okay. He's here. All right. Does anyone else come in since the color roll? Okay. So iso means the same. What did we just look at? That was a cubic structure. Sodium chloride, which is halide, it is a cube. What's the same about a cube? Every side is the same length. Isometric. The measures are the same. Okay? Another thing that has equal measure is an octahedron. Okay? This octahedron, every side is pretty close to being a perfect equilateral triangle. And there's 4 of these sides, okay? They form a square base, but that's not one of the sides, but every dimension here is the same. Octahedron. Octa meaning 8. 4 on the bottom, 4 on the top. So 4 is 8, octahedron. Here is a tetrahedron, a 4-sided crystal. Now, these aren't necessarily equilateral triangles, though they could be. Yeah, I guess it could be. Okay, here's one here, one back there, one over here, and one right here. 4-sided, okay, and all equal dimensions. And then this one's a real pain in the neck to say, the dodecahedron, okay, and that's, I think, a 12-sided figure, okay, and all of the lengths are the same. This is, the only way I could describe this is, it's not quite the same as a soccer ball, but if, you know, how the soccer ball is rounded, but if you had flat plates rather than the rounded parts, that would be close to a dodecahedron. I think that's 12-sided. Let me see. 1, 2, 3, 4, 5, 6, 7, 8. I think it's 12, okay? But each of the sides are the same, okay? Now, I don't think each of the angles are the same, but each of the sides are the same. So those are your isometric, equal measures, okay? Then we have hexagonal, and that's what we have here. A hexagon is a, how many sided? 6. 6-sided figure, and this has a 6-sided shape at the top, and usually is a prism, okay? But this is also a 6-sided figure, a hexagonal structure. The dimensions aren't the same, or else it could have been a cube, but it isn't. Some of these are shorter than others. They're not necessarily right angles, where cubes are, but this is a rhomda. In fact, I almost guarantee the angles aren't. Rhomdahedron. A rhombus is a equal-sided figure, but not equal-angled figure. So picture, if I had a box here that was a cube, and I sat on it, and it tilted over, that would then be a rhombus, no longer a cube, because the angles, some of the angles would be extended, and some of them would be shortened, made a cube, some obtuse, okay? The house we built over in Georgia is just a 2-bedroom bungalow that we have on the farm, so we have a place to go when we have to go to the farm. My parents died. We inherited, the 4 children inherited the farm, so I have a piece of it, but my brothers run it. But so when I go over there, their houses are too small, so I mean we could stay with them, but it's a little crowded. So we built a little 2-bedroom bungalow over there, and we built it in the middle of a cow pasture. And I wanted to fix it so that when we got there, we could open the gates and not have to open and close them all the time. But when we weren't there, it could be closed off and the cows could go back and forth without disturbing them, but it could be closed. So we put 4 posts, tried to get them equal distance from each other, but because of the angle, they weren't at right angles to each other. And my brother said, "Oh, you're having a square gate here." I said, "No, it's a rhombus gate." And he never used the term rhombus. And he laughed. "Oh, how's the rhombus gate going?" So what we do, we have them closed when we're not there. So they're closed here and closed here, so the cows can't get up into the house area, but the cows can go in between. But then when we're there, we open these this way and these that way, and then they close them off this way, and we can drive back and forth without having to get out and open gates. So that's my rhombus gate. So this is a rhomdahedron. Equal, the sides are equal, the angles are not necessarily. Okay, and it's a 6-sided figure, 1 on top, 5, and 4 on the side. A 6-sided figure. That's a 6-sided figure, but it's all equal sides, so it's an isometric. Here's another tetragonal structure, not like the tetrahedron, which is 4 sides, but this is a prism that has not equal sides. Obviously, you have triangles at the top and triangles at the bottom, and then rectangles in between. It's a prismatic structure, meaning it has a long dimension than the others, but it has 4 sides to it. Like a square here, but with triangles at the top. Here's an orthorhombic, and this again is a prism. Now orthorhombic, obviously rhomba is in there, so they could be close to equal sides, but not equal angles. But there's something else different about it. Some of the sides are equal and some are not. That's why I say I'm not going to get into all of it because I don't know all the differences. To me, that and that are not a lot different. Okay, but obviously they are. That's a hexagonal. This is not. Okay. Then the monoclinic, I have no idea why they call it monoclinic and triclinic. To me, this doesn't look far from being either of those two, but it is. Okay. So anyway, those are just different ways of that the surface symmetries are there to make these 6 different systems. Okay? And again, don't try to memorize these. This is not worth the effort to memorize. This is just so you get the general idea. Those are the crystal structures. And it used to be those pictures were in this text, but I don't see them in the text anymore. Maybe the older editions do have them. Okay? Now, before we move on, there are some pretty looking figures in your book that show some of these minerals. One's the salt on the top of salt shaker, okay? You can almost see those are little cubes, cubic structures there, like we saw before. Sodium chloride, cubic structure. There's 17.5, some large quartz crystals, okay, with some well-developed shapes. I can't think what the quartz are. I think some of those are tetragonal prisms and some may be hexagonal prisms. I'm not absolutely certain on that. Beautiful, beautiful, sharp designs though. I think more tetragonal. Not sure though. But then they have a mistakes, and misunderstandings. And most of the time these are pretty fun to read. But they're talking here about healing crystals. Okay, and you can read this and you can believe or not believe whatever you want, but he summarizes what he believes. There's no scientific studies that have found that crystals are beneficial, and so why they have them, I don't know, but evidently over time they've had a legacy, and I don't know why. Okay. Oh, here are a few of those. Here's that salt crystal. This is not the same picture as in the book, but you can see under a magnifying glass, or this might actually be a microscope, you can see just about every one of those crystals is a little cube. Now some of the cubes may have been worn off at the surfaces because they've been bounced around a lot and have a few imperfections, but these basically are your salt crystals. And this was the one that is in your book. These are some of the quartz crystals, and these are hexagonal prisms. That's what I wanted to call them, but they seem like they have some tetragonal structure at the top, but so I can't say for sure, but maybe they are truly hexagonal. Yeah, I guess so. 1, 2, 3, 4, 5, 6, yeah. Those are hexagonal structures, okay? You can see maybe better there, a little bit there. And I have some samples of some specimens that I've collected over the years. I can't remember where they all came from, but I'll try to show you that at the next lab. The next lab is a computer-driven lab. So what we might do is try to stay in this classroom and do the lab first, and then move to the other classroom and have the lecture. That's probably going to be Tuesday if we don't go to the planetarium. And for those who did come in late, I tried to contact Mr. Weigel both by phone and email yesterday, and I don't know if he's left me any messages. I was in class all morning, but he hasn't sent me back anything on email. So I'm assuming we probably won't go Tuesday. I think Thursday will be the earliest. Yeah.
I actually met with the guy today.
You what?
I actually met with the guy today that said he was supposed to come, and he was supposed to we were supposed to go see him.
Okay.
They had a transfer there.
Say that again.
They had a transfer there.
Oh, yeah.
And Sarah came up here, and I kind of talked to him about what was going on. He said, yeah, we were supposed to meet y'all, and he said Saturday night.
Okay, there's a couple things going on. There is a program that we have at Sanford on transfer stuff, and he's probably talking about that, not the planetarium. Oh, what did he say? Let's say the planetarium.
He didn't say, he just said we were Saturday night.
Yeah, I think that was that other program. I don't think it was us. I doubt if they use Mr. Weigel for recruiting this. They might. He's a real nice guy, but his job is a planetarium. So, but they might use him. I don't know. But I haven't heard from him, so he may be out of town or something. So I don't know when I'll hear. I will try to get in touch with him. I doubt if today's class will get over in time for me to call him, but I'll have tomorrow morning. I'll try to get in touch with him at when I'm on the Birmingham campus. It reminds me I need to, and I bet my work setting student's going already, to get the number and be sure I take it with me, because I have it in the phone book here, but I don't have it over there. Okay, so anyway, healing crystals. Not as many things, but that's beautiful illustration of some quartz crystals. So let's move to the next section, which is silicates and non-silicates. Now, does anyone know, what do you suspect about that word silicate? Does it make you think, oh, Brittany snuck in? Okay. We have very close to perfect attendance today. Missing Coco. You know if she's coming? Okay. Wow, wish everybody could be here. Anyone have an idea of where the word silicate comes from? Silicon is one. Silicon is an element. It's right below carbon in the periodic table. That would make it something like number 14. Okay? That's silicon. How about the 8? What does the 8 mean?
ATE means something with oxygen.
Absolutely. This has oxygens in it. In fact, it's SiO4. So, second?
Negative. What's the
Yeah, it's a negative
Is it?
3, I think. It's a silicate ion is SiO4 with a negative 3. So anything that has that in it is a silicate. So actually, you think it's silicon? More oxygen there than silicon. Okay? Not quite twice as much, even though there's twice as many atoms, but the silicon is a larger atom than the more massive atom than the oxygen is, so it's not quite twice the mass, but it's close to it. More than 2/3, I would say. So, what do we mention earlier about silicon and oxygen? Where do we see those two together? Oh my, where was that? Silicon and oxygen. Silicon and oxygen. Whoa! There it was. In the Earth's crust, basically close to 75% of the Earth's crust is made up of those two elements. Yeah, silicates are going to be pretty major elements in the Earth's crust. That's the point here. That's why they're given a special section here. Contain mostly silicon and oxygen, as Brittany read real nicely. No, she didn't. She knew that. Okay? And it makes up, the silicates make up 92% of the Earth's crust. If it's not all silicon and oxygen, it's got something mixed with it. Okay? I mean, silicate, something mixed with it. Calcium silicate, potassium silicate, iron silicate. There's silicate somewhere in all this, in a lot of the stuff. 92% of the Earth's crust made up of silicates. Based on a silicon-oxygen tetrahedral unit. Tetrahedral means 4 sides. Okay? Now, what's the 4 sides here? You have a silicon in the middle and 3 oxygens around it. So SiO3. The ion is SiO4, but the silicate is maybe it's SiO3. 1 iron here, oxygen here, 1 here, 1 there. So this forms a little triangle, these form a little triangle, that forms a little triangle. 4 little triangles, tetrahedral unit. The silicon in the middle. Okay? And remember when I was mentioning the clay? The clay is one layer of silicates, another layer of aluminate, which is a hexagonal structure. And then some silicates have a second silicate structure, a layer at the bottom. Others are just 1-to-1, some are 2-to-1. We'll get there later. 4 major arrangements of these silicates. I think this next slide, I'll go over here to hit the slide. This is the first of these. Oh, no, here is the tetrahedral unit. Here's the silicon in the middle, 4 oxygens equally spaced around them. Each one of these makes a triangular plane, 4-sided. Okay? That is your silicate structure. Tetrahedral unit. Tetra means 4, hedrals, basically planes, I think it is. Okay? Now, there are 4 major arrangements of these. I hope that's the next slide. Yeah, here they are. The first of these is the tetrahedral structures, just like we just saw. Now, if you were listening, you heard me say that the silicons are more massive than the oxygens. That doesn't mean they're bigger. That means they have more mass. Okay? Now, that sounds like it's contradictory, but when I say bigger, I mean volume-wise. Now, here's why that is. Usually silicon is a plus ion, normally. So that means it has deficit of electrons, so meaning the extra protons in the middle are pulling those electrons are around it closer, making a smaller atom. Whereas oxygen is usually a -2, meaning it has extra electrons, meaning you have more charge there, so the electrons get to go further away from the nucleus. So even though it's more massive, the silicon is a smaller volume, and then the big old balls of oxygen around it. And that's basically why they drew it to look like this. The silicon is the green in the middle, and then you have the 3 base oxygen, big old balls there, and then one on top. And that makes it, and then they connect to the centers to make these prism-looking things. So this is your tetrahedral structures. Individual tetrahedrons, that's the first of your, and that's what we call the isolated tetrahedrons. Okay? That would be close to what you see in sand particles. And that's why they hurt when they get in your shoes, and rub on. That feels like it's a chunk of stone in there, and you get it out, and it's this little big crystal. And you think, how could that hurt so bad, Yeah. Well, second thing they do is the chain silicates. Now, what happens here is that one of these oxygens, I think it's that one on the bottom there, not that they're really on the bottom, it gets shared with 2 of these. And then here's one on the bottom gets shared with 2 here, 1 here. It's not a straight chain, it's sort of a wiggly chain, but you have to have it because of that crystal structure. Now, can one think of a chain silicate that's pretty dangerous to be around? Now, you may not know about this yet, but you do without realizing you know about it. Asbestos. I'm pretty sure asbestos is a chain silicate. We'll check. I think it's going to come up later. And these asbestos, because of the fibers and the very small structure, you breathe those in, it damages lung tissue, and you get asbestosis, which is a pretty bad, serious disease that really destroys lung tissue and that cripples people. Okay? Y'all know of anyone with asbestosis?
I have to be tested for it.
He has. Oh, yes, yeah.
Do you work at US Steel?
Yeah. Now I was going to say. Next question. Well, where did he work? Because actually, some auto mechanics that used to work with the brakes had asbestos in them before they knew it was dangerous. Asbestos. Second.
I used to be a mechanic.
Yeah. Okay. The asbestos was a wonder material when they discovered it. It could get as hot as you could and never burst into flame. They thought, wow, what a fantastic material. It's durable. It's flame-proof. It's an insulator. I mean, it does everything well until they found out it killed you well, too. It really. And now, forbidden to be in anything. even though there are some types of asbestos that are not harmful at all. They do not cause asbestosis, but because people can't distinguish them, all asbestos is considered bad stuff. Okay? I think we'll mention that a little bit later in the text. Okay, so that's the second, the chain silicates. Then we have the sheet silicates. And that would be like this. Now not only are they sharing one oxygen between two silica, they'll share two oxygens between two silica. In fact, in some places 3, okay? So, yeah, now you have a sheet silicates. And that's what I was talking about with your clay minerals. Kaolinite, I mentioned in pencil lead. That's a 1-to-1, a silica sheet, alumina sheet. Silica sheet, alumina sheet. There are others like montmorillonite, bentonite. Some of these are 2-to-1 clays. 2 sheets of silica with alumina sandwiched in between. Those are your sheet silicates. And then they have something they call the framework silicates. And I don't find this a particularly great picture for this. And I don't even think they're really representing what they're saying there. This to me is another sheet silicate, it's just a bigger sheet, okay? This is almost still one dimension, but it is a sheet. But the framework silicate would then have others on top. You share some of these top ones. And that's sort of what goes on in the clays, only those are, the oxygens are being shared between aluminates and silicates. But if you had silicates piled on each other, then you would have what they call the framework silicates. Which I'm guessing your quartz is definitely 3-dimensional. So that may be a framework silicate. I came over here to press the button again. Old dogs don't learn new tricks well, do they? All right. In the crust of the earth, how much of that is made up of what's the most prevalent type of mineral? In the crust of the earth. What was the last slide? Earth to class, come in, yes. Silicates. How much of the Earth's crust is made out of silicates? 92%. That's most of it, folks. Big time. So all the rest of the minerals on the Earth's crust are classified as non-silicates. And how much of it is that? 8%. And yet they have all these different classifications for the little 8%, whereas the silicates, they just have 4 sort of classifications. So yes.
Sorry. So now that's why they are afraid to use silicates for anything. Because I was just about to ask, like, since it's 92%, how come we don't try to use, those resources instead of others that are depleting?
Okay. And exactly what do you mean by that? You mean why don't we mine for silicates rather than iron?
No, I was saying now I know why.
I see,
But I was
right.
saying, is there any other way, or is that just it? Does
Okay.
it always create that? Because I know you said you can't tell the difference, but is there like a way that we could tell the difference? Is there, I don't understand. Is there a chemical reaction that happens to form this?
To form what?
Like things that cause, cancer.
I see. Back on the asbestos.
Uh-huh.
Yeah, people know which ones are good and which ones aren't, but generally there's been such a scare about it. If someone sees asbestos, no, yeah, even though it might not be. We still use it. People still use it. Like, for instance, the floor in the home that I grew up in Georgia, I remember we laid that floor, okay? My dad was a farmer and he was real thrifty, let's put it that way. Cheap is another way, but thrifty is a nicer way, okay? And actually, he contracted for the frame of the house to go up, and the plumbing and electrical, that kind of stuff. But all the interior stuff, the flooring, he had the subfloors done, but we laid every piece, mostly him, but every piece of pine flooring, oak flooring, sheetrock on the walls, paneling on the walls, everything. Now, the cabinets, we hired that done, because that was a little more special what he did. But we did it, I was a little kid, I was holding a device he put together so I could hold the sheetrock up so he could nail it in. I mean, I remember doing that as a kid. It was, we built the most of the house. Well, the flooring that we put in the kitchen and den, my uncle had found it, he was cheap too, on sale, his brother, okay, on sale somewhere, and he combined the colors, couldn't find all one color, so he found 3 different colors, combined them in a pattern that I thought was pretty neat, and the colors went together okay. But that was later. Now my sister has that house. She's scared to take up the floors because back in those days, those heavy duty, and this was like industrial tile that he put down. That industrial tile was really long lasting and fireproof and stuff, and she's afraid it has asbestos in it. So she won't take it up, even though it's really worn by now. And we tell her, just put something over it, it'll be safe. But to take it up, you may be exposing fibers. I don't think it would be dangerous, but she's afraid it would be. So then just have them put another floor on top of it, and then the fibers can't escape. So, but anyway, so no, people don't know, they just panic. And it's not, it's just the way people are, I guess, I don't know. All right, non-silicates. This means there's no silicon-carbon tetrahedrons in the crystal structure at all. Only 8% of the Earth's crust has these non-silicates, but they are pretty important. Okay? 8 major groups, and the most abundant of those 8, which probably is only a few percent, is your carbonates. And I already mentioned that. What's one of the carbonate minerals that we have? Limestone. We are under Lane in Alabama. Fortunately, limestone is a pretty nutrient-rich parent material, so therefore our soils are better than the ones in Georgia. Georgia's underlain by granite, which is not very rich. It's mostly a silicate, okay? So the carbonates are the most abundant. The 2 major carbonates we have are these are stones. They're limestone and calcite is calcium carbonate, and dolomite is a mixture of calcium and magnesium carbonate. If you have a choice of which to use, the calcite is cheaper. When you have lime, that you're trying to lime your soil, maybe you have too acid of the soil, it's not growing good vegetables, you want to bring down the acidity, they'll sell you lime to do that. Calcium carbonate, calcite, is fast acting, but it only has calcium and carbonate in it, okay? Well, dolomite has calcium and magnesium carbonate. There's plenty of calcium nutrients out there. Plenty of them. There's never a shortage of them. Magnesium, though, there is a little bit. What? Probably I should hit this later, so we'll hold off on that. But those are the 2 kinds, calcium carbonate, magnesium carbonate. There are other carbonates, we have that, okay? Sulfates. Does anyone know of any sulfates you might have run into before? I don't know of many people that use these now. I know we have some at home, because my wife read about it would be good for one thing. But has anyone ever heard of Epsom salts? Yes. Okay. Huh?
You make drugs out of it.
Oh, you do? Okay.
Bath salts or Epsom salts?
I just use it for my muscles.
Okay, exactly. I was going to say my grandmother used to soak her feet. She had some gout in one of her feet, and she would soak her feet in Epsom salts because it just was pretty good to do that. Whether
it relieves the pain,
it really does,
and it helps to release your muscles
yeah.
so you can stretch.
Okay, so Epsom salts. That's let me get it right now. That I believe is magnesium carbonate. Yeah. Another sulfate that I don't know if you've heard of, gypsum. I mentioned. Yeah, do you know about it? Where? What's that?
It's supposed to be good for planting.
Second.
He said it's
Yeah, okay, very good. Agricultural answer, I love it. Okay.
My dad had a farm, so.
Did he grow peanuts?
Well, government had him got him to sharecrop it with them, so
Uh-huh.
they paid him.
Right.
I
Okay.
think his dad did grow peanuts. So.
Yes, and peanuts, that's one thing gypsum is used for. And the other thing, and I already mentioned it today, just in passing not long ago, when I talked about sheetrock. Do you know what I mean by sheetrock? That's a brand name, by the way.
It's like
Say
kind
again?
of flooring.
Well, not flooring, walls, mostly. It would be too soft for flooring, but walls and ceiling. This doesn't have sheetrock. They have another name for that. But some of the classrooms that you don't see the block in, that's probably sheetrock. Now, actually, that's a brand name. The generic term for that is gypsum board, because it has gypsum sandwiched between heavy cardboard that takes paint well. Okay.
I think my mom got some of that in her house.
I bet so. Oh, I bet you every house just about has sheetrock or gypsum board in it. It's just ubiquitous all over the place. Okay. The older houses might have what did they call it? Plaster, which had some gypsum in it too, but that they put on with the trowel. But the more modern houses, they put up these 8x4 sheets of sheetrock or gypsum board. Yeah, I've done that. Mudded it. Ooh, nasty job. So that's calcium. Let's see, what should I say? Yeah, it's calcium carbonate. Gypsum is calcium carbonate. Going back to the agricultural thing, the reason I said peanuts require a fairly neutral soil, a little bit acidic. They can't be too basic, okay? Which makes good for the South, because we have pretty acid soils down here. But they also require a certain amount of calcium. Now, most of your calcium source is usually calcium carbonate, which raises the pH, which makes for a basic soil, which the peanuts don't like, so they don't like to use that. The other place you can get calcium is from gypsum. They call it land plaster, and that's calcium sulfate, which calcium sulfate is neutral. Calcium slightly alkaline, but sulfur is pretty acidic. Okay, sulfate is pretty acidic. So actually, that is a great balance for peanuts. And so they put gypsum, which is land plaster. That's the old farmers used to call it that. They put that on. Now, why do peanuts need calcium? Well, all plants need calcium, but peanuts especially do. Can you think of another plant that's very close to peanuts in nature?
Avocado?
Say again?
You said
Very similar to peanuts, biologically. Say again?
Potato.
Okay, you would think that because they both grow underground. But actually, your peanut is a legume, like peas and beans. Actually, the thing I think it's closest to is soybean. The soybeans grow on bushes up here. Peanuts are underground. But you see, the peanut has to bloom, and to bloom, it sends up this thing, little peg. It blooms, it gets fertilized just like a soybean would, but it's just above the ground. I'm sorry, the blossom comes up in the stem, and then as soon as it gets fertilized, then it ducks back under. They call that pegging. Peanuts will not peg unless they have enough calcium. So that's why they use it as land plaster. Peanuts. The peg, because the nut or the bean, the peanut grows underground, but it has the blossom above ground and goes back under to do its thing. Okay, so yeah, sulfate. Two major types: calcium sulfate, gypsum, magnesium sulfate, Epsom salts. There are others too. Oxides. Just about everything will oxidize. Not everything, but a lot. Name some things that will oxidize.
Rust.
Rust is iron oxide. Absolutely. Okay. Aluminum oxide. Just about name a metal and you can have an oxide with it. Just about always. And the oxygen also combines with the H, carbonates. Yeah, everybody. Carbonates, CO3, sulfates, SO4, oxides are just O's. All of these, not all of them, but all those have oxygen all over them. Okay? Sulfur dioxide, nitrogen oxides. It's just oxides all over the place. Okay? Sulfides. Well, what sulfide is a lot like oxide. It's something else with sulfur, just like oxide is iron with oxygen. A sulfide is iron with sulfide. Sulfur. In fact, there is a type of iron sulfide that is sort of infamous, maybe famous, but more infamous. Iron sulfide has a mineral name. Boy, I can't think of the name now. All I can think of is the common word. Pyrite. Pyrite is the mineral name. You know the common name for that? Fool's gold. It looks like gold, but it's not. No, it's not. That's iron sulfide, which is pyrite. And then there's chalcopyrite that has some copper in it and stuff like this. The halides. Now, I mentioned this before, too. We already mentioned one halide. Which was that? Table salt. Yeah, NaCl. That's the halide. Your halides are the things that have the second mineral element is the group 7. Okay? Oxides have something else in oxygen, like iron oxide or whatever. The sulfides have something else in sulfur. The halides have something else and one of the group 7s. Fluorides, chlorides, that's salt. Bromides, iodides. You don't have much of tinamides or whatever the others are. They're very rare. But those are your halides. Group 7. Okay? And then another 8. Phosphates. Where are phosphates important? Anyone know?
They have to do with phosphorus.
Say again?
They have to do with phosphorus.
Yes, it has to do with phosphorus, absolutely. It's phosphorus with oxygen. So 8 means oxygen. PO3 or 4? 3, I think it is. PO3. Okay? I thought since you had agriculture answer before, you'd have it now too. One of the 3 major nutrients. Nitrogen, potassium, and phosphate. Phosphorus.
Yeah, I was trying to get someone else.
Yeah. So the phosphates are there too. Except that really the plants don't need as much phosphorus as they do nitrogen and potassium. But it's so hard for them to get it, you have to add a lot to it because it all mineralizes so fast that the plants can't get to it. So that's why it's important to get to it. The major phosphate mineral is called apatite. It's not that it's hungry, it's with a I rather than E or something like that, but it's spelled just slightly differently, but that's the major one. A lot of the mining for this was done down in Florida. That's the central ridge in Florida. Florida is not very high, it doesn't have much of a ridge. Right down the middle of the peninsula, Lakeland and Bartow, Florida, Polk County, Florida, a lot of phosphate mining there. The sad news is we've used most of it up. They're easy to get to phosphates. Where are we going to get phosphate after we do use that all? I mean, they're digging deeper and deeper and getting less and less and lower quality. What are we going to do with agriculture using it at the rate that it is? What are we going to do? And I mean, it's a big question. Because we had the Green Revolution that came about that enabled us to feed most of the people on the planet. And what that was they found a way to synthetically make nitrogen fertilizers by producing ammonia. Okay? I mean, ammonia occurs naturally, but they found a way taking methane gas and I guess just nitrogen, okay, that's in the air, and under high temperatures, forcing them together to form ammonia. And ammonia is a great source of nitrogen. So they made ammonium nitrate and all sorts of other ways to do it. Before that, they used naturally occurring nitrogen, nitrate, sodium nitrate, which they mined, but we used most of it up. And by the way, sodium nitrate, anyone know where that comes from? Bat poop. I mean, they call it guano.
Guano.
Yeah, guano. Yeah, and it's fat droppings that are mineralized and form sodium nitrate. But they use most of that up, and then they synthesize the nitrogen, because you have nitrogen in the air everywhere. Synthesize it with methane, which is a hydrocarbon gas, a fossil fuel. So that made it sort of expensive. The process is expensive, but that's what created the green revolution. And without that, the world population could not exist at the level it does now. We did not have access to that kind of fertilization. Now, you would think that the chemists that came up with that should have won a Nobel Prize, wouldn't you think? Because that has changed the world, literally. That process of combining methane with nitrogen to make a usable nitrate fertilizer, relatively cheaply, but lots of great quantities of it, that's called the Haber process. Haber, named after, I think his name was Franz Haber, who was a chemist, German chemist, okay? And yet he is more infamous than he's famous. Now, why would I make a stupid statement like that? It seemed like he would be one of the most widely respected and appreciated names on the planet, and yet he's not. Because he was a German chemist in the 1930s and 40s. Oh, guess what else he made?
Okay.
He developed all sorts of poisonous gases and really evil chemical compounds that they tested on the Jews and the other people in concentration camps. He was right in there in the thick of it. He was the main chemist that did all that. So even though he produced one of the most life-giving inventions of the last century, he is not honored at all, because he also took an awful lot of lives with his chemistry. Sad situation. Okay. So those, how did we get up to there? Okay, phosphates. Then you have hydroxides. Actually, I mentioned some aluminum oxides, but actually you have more aluminum hydroxides. Remember I said sodium reacted with water. It forms sodium hydroxide. So you have other chemicals called hydroxides. And then the last of the non-silicates are your native elements. Gold, silver, copper, those kind of elements that just basically exist either by themselves or occasionally combined with something else. Like copper will be copper sulfate sometime, and that's sort of a greenish color. So, but most of your native elements or your ores are also non-silicates. They don't have silicon in them because they're elements. Okay. A lot of slide for 8% of the Earth's crust, huh? Okay. And the iron ore would be one of those native elements. Okay, silicates and non-silicates. I thought it was going to come up. All right, here we go. This is a table. It's in your text. It's greenish in your text and sort of brownish here. But this shows exactly the last things we were talking about. Your minerals, silicates, non-silicates. Actually, it should be silicates, non-silicates. Heavy on that side, light on this side. 92% over there, 8% here. Of the silicates, we have three classifications. Ferromagnesium. Can anyone find two elements in that name?
You said what?
Ferromagnesium.
Iron.
Iron. The ferro comes from iron. What's the symbol for iron?
Fe.
Fe. So that's what this is. Iron, magnesium, silicates. Okay? And then the non-ferromagnesium silicate. We have silicates and non-silicates. We have ferromagnesium, silicates, and non-ferromagnesium silicates. Either it's got iron and magnesium or it doesn't. Okay? And then we have the clay minerals. Clay minerals are a little different. We'll get to that. The ferromagnesium silicates are mostly deep in the ground. We have some places like Birmingham and Bessemer and some of the other areas where they've made their way to the surface in larger than normal quantities. But some of the minerals here, you don't have to know these, but just sort of recognize them. When you see them, think, oh, high iron content. Biotite, hornblende, augite, and olivine. Now we'll see on a later slide some relations between these, but those are your major ferromagnesium silicates. Mostly occur deep in the earth. Some occur near the surface, mostly deep. Okay? The non-ferromagnesium silicate, now get this, here's the key. Iron is heavy, so therefore it's going to be usually deeper. Okay? Also, iron is denser, it comes out of solution sooner, deeper. Okay? The lighter ones, and when I say lighter, lighter weight, but also lighter in color. Non-ferromagnesium silicates would be quartz. What's quartz made up mostly of? Silicon dioxide. Very light, light-colored, lightweight. Quartz, silicon dioxide. It has other chemicals in it, but mostly that. Muscovite, which has potassium in it. It's also called white mica. Okay? We don't have much of that down here. Your feldspars, which are aluminum silicates, not ferromagnesium, but aluminum silicates. Now, among those feldspars are several classifications. Plagioclase, which is a sodium feldspar, which is sodium aluminum silicate, or calcium feldspars, which are calcium aluminum silicates. So all your feldspars are aluminum silicates. Those are two of the major. So those are your two plagioclase. Now again, you don't have to know all these terms, but just sort of recognize them. Those mean your aluminum silicates. Orthoclase is another one, and that's your potassium feldspar, potassium aluminum silicate. So you have two types of plagioclase, sodium and calcium, one type of orthoclase, potassium. And these are your non-ferromagnesium silicates. Quartz is mostly silicon dioxide. Muscovite has potassium silicates. Feldspars are aluminum silicates, and you have sodium aluminum, calcium aluminum, and potassium. Okay, clay minerals. What is it that makes a clay? It's sort of the same type of thing that makes a sand. It's not a mineral. It's a particle size. A sand, if I have one. Okay, I have a dime. Well, I have at least two dimes. No, one dime. Okay, a dime is about 1 millimeter thick. Any particle, really kind of particle, that is 2 millimeters down to just a fraction of a millimeter, that's going to be a sand. Then you have a silt, which is sort of a floury-like substance, very small particle size. And then you have a clay. Now, what is a clay? Take this dime and slice it into 1,000 equal slices. Can you imagine that? Submicroscopic. Okay, you can't even see it with a microscope. That's that thin. Two of those together is the largest size clay particle you'll ever get. So anything 2 microns, that's what micron, 1,000th of a millimeter is a micrometer or micrometer, okay? And 2 of those and smaller, that's going to be a clay particle. So clay means a very small particle size. Now what do we know about clays? They're slicker than snot, aren't they? I mean, if they get wet, it's hard to drive over them, you fall down in them, they get messy on your clothes. That's because they're very small particle size, and it's hard to wash them out of your clothes because they adhere so tightly to the fabric and stuff. They're tiny. And I mentioned this one before in pencil lead, kaolinite. That's a 1-to-1 clay, 1 layer of aluminum silicate, aluminate, and 1 layer of silicates. Okay? 1-to-1 clay. And illite is a 2-to-1 clay, and basically an illite comes from muscovite. Muscovite is a big mineral. When it breaks down and becomes very small particle size, it changes to an illite, a clay particle. Chlorite is a sometimes called a 2-to-2 or a 2-to-1 clay that actually swells a lot, and there's others that swell even more, but that's another kind. These aren't all the types, but these are the most common. Kaolinites are very common here in the southeast. Most of the clays that exist here, in fact, there's some places in Georgia that they do kaolinite mining. They get great quantities of that, and it's used for all sorts of things. Not just pencil lead, so it's certainly used there, but basically, this paper, you feel it's a little slick, that's because it has a kaolinite coating on it. So your magazines have probably even more. Writing paper, on the other hand, has a little bit less, but it still has some because the kaolinite from the pencil lead and attaches itself really to the kaolite there, and they bond together really well. It makes the pencil lead stick better. So yeah, you have kaolinites, all sorts of uses. Coatings mostly, okay. But also there's some medicines that you have that in it. Anyone think of one? Kaolinite in it. Kaopectate. You ever heard of that? Is that milky stuff they give you if you have an upset stomach? Yeah, okay.
Pepto-Bismol.
Yeah, Pepto-Bismol is the peptide part of it, yeah. But it probably has kaolinite in it too. Why? Because these are tiny, tiny, tiny little particles, so they have a lot of surface area, and they can absorb those toxins or whatever it is that's upsetting your stomach. And they will clog you up if you take them too much, because that's what they do. They absorb the bad stuff. Okay? So, those, and by the way, the clay minerals, the other thing special about them, usually those are things that came from here or anywhere else when it weathered away and degraded to very small particles and then reformed to be these silicate minerals. So actually these have been broken down physically and reformed chemically. Okay? Most of your clay minerals are like that. So let's look at the non-silicates. We already mentioned these. The carbonates, this is why I said I jumped into it too soon. Two major types, the calcite, which is all calcium carbonate, and dolomite, which is a mixture of calcium and potassium chloride. And why that is the better lime to use if you're growing vegetables or something like that, okay, is because all plants have enough calcium. I mean, there's plenty of it out there. It's just all over the place. Have you ever noticed your potted plants, how your clay pots will get the white crust around it? That's calcium that they're not using, and they just get out and it evaporates away. Okay? Whereas magnesium, plants always need magnesium. And you know what the major reason they need it for?
Oxidizing.
Second?
Is it oxidizing?
Yeah. Let me explain it this way. What makes a red blood cell red? Okay, oxygen oxygenates, but what does it oxygenate? What's in the middle of
The cell.
the central atom in a red blood cell? And what do we use to measure how good your red blood cells are? We measure your hemoglobin and hematocrits. You know what the major element is there? What do you take if your hemoglobin's low? Iron, exactly. That's the central element in hemoglobin, is iron. And iron oxidizes. And guess what? There's two types of iron oxides. One is called ferric oxide, and one is called ferrous oxide. The ferrous is FeO, one iron, one oxygen. The ferric oxide is Fe2O3. So 3 oxygens for 2 irons. Ferrous oxide is called reduced iron. It's a grayish color, almost bluish color. I can remember when I was growing up, when we moved to Georgia, in the house that my sister has now, the field there was a red clay field, Georgia red clay. Yeah, it was red field when my father would be, preparing it to plant. But at the bottom of that hillside was sort of a swampy area, and it was grayish colored soil. And I thought it was just the sand is washed off the hillside down there, and that's why it's grayish color. It had plant material in it, give it a little color. But I found out that wasn't the case. The swampy area down here, because of the water all around it, that iron that was, and guess what made the hillside red? Rust, or iron ferric oxide, the highly oxidized iron, red, okay? But down here, where it had been underwater parts of the year, that was ferrous oxide, because that was reduced iron. The oxygen, it couldn't get as much oxygen as it could up here. It was the same amount of iron, basically, but this was ferric oxide, this was ferrous oxide. Where does that occur in our bodies? We have two types of blood vessels, veins and arteries. Now, not always, but most of the time, the veins are blue, the artery is red. Okay? Why? Because the iron in the hemoglobin, when it's reduced, like we've used it up, it turns to ferrous oxide. Low iron, low oxygen. And it is returned to the lungs, and in the lungs, it's oxygenated in the capillaries around the lungs. It becomes ferric oxide and returns to your muscles as arterial blood, which is red. Okay? That's happening all the time. Now, you don't see your arteries. You know why? They're always deep. That's the oxygen-rich blood. You don't want to, if you get scratched, to lose it. If you get scratched, it's probably going to be venal blood. And it may be blue to begin with, but as soon as it's exposed to air, it turns red. And if you've ever seen that happen, you know that's the case. So that is happening here too. Okay? What got me off on the... Oh! Okay. Long way around here. We're going to get to that in a minute. And by the way, hemoglobin, hematite, iron oxide. Same root word. Okay? But getting back to our blood, hemoglobin in the blood, the central element in there is iron. There is a very similarly constructed cell or compound in a plant. Very vital to the plant's life too, and frankly very vital to our life. What's the most vital characteristic of a plant? What's the major thing they do for us? They what? Yes, they take in carbon dioxide and give off oxygen. Okay? And what piece of a plant does that? The what? In the green leaves. What makes the green leaves green? Chlorophyll. That chlorophyll structure there is that it's a little claw, just like iron, hemoglobin is a little claw. Except the only difference in hemoglobin is iron, and chlorophyll is magnesium. And that's why plants are much more favorable to use dolomitic limestone, because it provides the magnesium that every green plant needs. And there's plenty of calcium out there, so give it some. That dolomitic limestone is more expensive. It's not as good of a limer because it's really hard to grind down. It's a small particle size, so it makes it easy to. It's a tougher molecule, but when it does break down, it releases magnesium. Okay, so those are your carbonates, your sulfates, or your gypsum, and they mention anhydrite, but I like to use Epsom salt. I like it better. Okay, anhydrite, whatever that is. Gypsum is calcium sulfate. I'm not sure what anhydrite is. The oxides, hematite, iron oxide, magnetite, iron oxide. Hey, wait. Why do we have two iron oxides here with different names? It's the first 6 letters of that. Magnet. Iron oxide that is naturally occurring magnetic that's magnetite, identically chemically, is hematite, which has no magnetic characteristic. Okay? So that's why the two. They're identical chemically, but this one's magnetic, the other one's not. I think that's limonite. I can't read it here, but I think that's limonite. And then you have aluminum oxides. I mentioned those before. Your sulfides, pyrite, what do we say it was? It may glitter, but it's not. Fool's gold, exactly. Okay? Sphalerite, whatever that is, galena, and then chalcopyrite, which it looks like it would have calcium in it, but I believe it has copper. Strange that it has that name. Phosphorus, a major mineral that contains phosphorus, is apatite, with an A, not an E. Okay? It's not that it's hungry, it's apatite. Now, how they take that mineral, apatite, if they were to grind that up and spread it in your field, your plant's going to get very little phosphorus out of it. They have to really break that mineral down. What they use is a really strong mixture of sulfuric acid. Okay? Now, there's something, any of you are familiar with a company called Drummond Coal? You know, they're a big, major company and involved in a lot of things. And something they do here with coal produces a lot of sulfuric acid. I think what they do, they're taking the sulfur out of the coal, and it comes out as sulfuric acid. I don't know the whole procedure, and it may be, industrial secret they don't want to let out. But somehow they do it. So they make a lot of sulfuric acid here, and they don't want to dump it out somewhere. They send it down to Florida, and they do a lot of the apatite mining, the phosphate mining down there, and they use the sulfuric acid from up here to break down the apatite mineral so they can use phosphoric acid that then they use in fertilizers. Okay? It's sort of because I used to see some of the same tanker trucks here show up down in Florida when I was working on radon research there in those areas where they had phosphate mining. The halides are halite, which is sodium chloride, and fluoride, which is probably sodium fluoride. Okay, that would be fluoride. Those are just two of the many halide chemicals. Then your native elements: gold, silver, copper, diamonds, sulfur, elemental sulfur, anything that exists just as a pure element. Okay, your ores, basically. Even iron. There's not just much pure iron. Most of the iron is either hematite, magnetite, or one of these over here, high iron content. You have to break it down. Okay. Any question on that? How are we doing time-wise? I got 15 minutes, technically, of... Okay. Here are some sample pictures, some pretty nice pictures of some of these. Oh, and here's some of the characteristics. I didn't go into this much. Please read the text. Nothing replaces reading the text. The slideshow is not going to do it. Some of the big differences, let me get my screen over here. Some of the big differences between the ferromagnesium silicates and the non-ferromagnesium silicates. I said it, I sort of mentioned it in passing. These are heavier. These are generally lighter. These are more on the crust. These are more deep in the earth, mantle and core. But the other main difference is the color. The density of source is there. The heavier, the more dense it is, but also the color. Most of your iron minerals are dark colors. Most of your non-ferromagnesium magnesium silicates are lighter color, clear to white, pink, something like that. So, color is important as a classifier. These, what would you expect? Ferromagnesium silicates. Augite, I think, is way over here. That's, I think, really heavy in iron. Hornblende, to the left, okay, pretty dark. Biotite, compare, okay, yeah, I'm sorry, I'm misreading this. Compare the dark colors of the ferromagnesium silicates, augite, hornblende, and biotite, to the lighter color non-ferromagnesium silicates, which are over here, which are basically your mica. Which one's a mica? I think this is a mica. Okay, mica front center. These are the micas. White and pink orthoclase. I think that's the white and pink orthoclase. Okay. Top and center, yeah. And quartz. Okay. These are your quartz. You see that? There's that hexagonal structure there. There's the quartz. Compare that to the darker ferromagnesium over there. So a key component here, the dark color usually indicates high iron content. The lighter color, and that means more ferromagnesium silicates, and the lighter color are your non-ferromagnesium silicates. And by the way, mica, this down here, remember it? That's a potassium silicate. We don't see much of this here, but in the Midwest they have, I think, a fair amount of it. Back before glass was commonly made, what they would do if they could find pieces of mica, mica comes off in sheets, okay? Basically what happens, the potassium gets dissolved out and that leaves the sheets separate from each other. You can peel them off. Now this doesn't show you doing that, but what they used to do is peel off those sheets and frame them up and use those in the windows. They weren't transparent like glass, but they were translucent, letting a little bit of light in, and you could sort of see if there were shapes outside, you know, but it would, that's what they used for glass back when they were building the old soddies out in the West. Yeah. What?
Because it's called stained glass. I was thinking about like the like Catholic churches and things like that, like older churches, how they have like the stained glass, but
Right.
glass.
Oh, and
So
I'm glad you mentioned that. That's what I was saying before about glass. What did I say? It has really no crystalline structure because it was cooled very quickly. So actually, it's not technically a crystalline solid. Actually, what they call it is a supercooled liquid. And one of the illustrations of that, the very old cathedrals that had the stained glass or the cut glass windows in Europe and the cathedrals and stuff, if you were to go and measure those of the oldest ones, you'll find the glass at the top is much thinner than it is at the bottom because it has no crystal structure, so those molecules over hundreds of years actually are pulled down by gravity. So actually, it is a supercooled liquid. It's not really a solid, crystalline solid. It has its own shape pretty much, but it doesn't. Now, our house was built in the 1930s, okay? We like old things. I'm glad my wife likes old things, so she wouldn't have married me. But anyway, that's beside the point. Okay, but the old glass in our house is only very few panes, and you can tell which ones have been replaced because the older panes are wavy. Now, maybe they just didn't have as good a glass making techniques, or maybe they were cheap. I don't know, but it also is that it's altered over time. Where the new panes were nice, clear, you just look through. But when you go through our living room and look out the window, the trees sort of ripple a little bit because, All right. They do show a picture in the book of you peeling off some mica. I knew I'd seen it somewhere. I thought it would be on the slide, but it wasn't. Okay, now let's look at the physical properties of minerals. And we've already sort of hit on some of these. First physical property you'd probably notice of any mineral, because you notice it, you see it, is its color. Is that a good thing to classify a mineral by? Probably not. You have diamonds that are clear, crystal clear. They're the best diamonds. You have pink diamonds, you have chocolate diamonds, you have all kinds of different kinds of diamonds that have just slight impurities in them, but they're still diamonds. So, but they can vary in color big time. And when you do the next slab, you'll find out the color varies all over the place for many of these. So it's not a very useful, it is a physical property, but not very useful for classifying. It can be influenced by just trace amounts of impurity, change the color completely. Now, this is a strange thing. Actually, something better than color is streak, which is related to color. But what streak is, you take a piece of something like sandpaper or something else that's pretty rough, you take the mineral and scrub it across that, and it leaves a streak on there. That streak color is much better classifier than the actual color. Because what might appear to be pink, that would have just a trace amount of impurities in it, and it goes all the way through it. But when you do the streak, you get the predominant thing, which would be part of it. So it's the color of the mineral and finely powdered, which is a much better indicator of the mineral than the color is. Much more consistent in its predictiveness than color. Now, a couple of you have mentioned this already when we were talking about diamond. Hardness is resistance to scratching. And there is a scale, a guy named Moe, and that could be a potential paper topic, who in the world was Moe. It wasn't Larry and Curly's friend. That's not one, okay? But this is the Mohs hardness scale that he came up with. You could write a paper on the scale, how he developed it, whatever. It uses 10 test minerals with increasing hardness to classify other minerals, okay? And here are those 10. The very softest mineral that we have in the classify, and some of you ladies, and maybe some of you guys too, might use this, talcum powder. Can you get much softer than that?
What?
Talcum.
Talcum?
Yeah, talc.
Acidic.
Yeah, basically a lot of your cosmetics, if they're in a base, they're in a base of talcum. Yeah, it's very smooth to the skin. Soft as you can get. That's talc, a mineral named talc. Next was gypsum. Remember the gypsum board? Actually, if you get that gypsum board, now that's synthetic, but if you can scratch it with your fingernail easily. Not the paper part, but if you cut it and see the sandwich in between, that's the gypsum, you can scratch that with your fingers very easily. Okay, that's number 2 on the hardness scale. This is the Mohs hardness scale. Calcite, and we'll see an example of that. I'll show you some. Actually, I had a student in this class several years ago who was also a coal miner. Okay, young guy, but he worked in the coal mines, but he's trying to get an education too. And actually, I didn't realize it until he told me calcite forms in the same type of areas that coal does. And he brought me some really pretty minerals of calcite, examples of calcite. Fluorite, we mentioned that as one of the non-silicate minerals that is a halide, okay? Calcite was a non-silicate mineral, which is a carbonate. Gypsum was a sulfate, okay? Talc, I don't know what that was. Apatite was a phosphate, okay? Orthoclase, that's one of the ferromagnesium silicates, okay? No, I'm sorry. It was a non-ferromagnesium silicate. It was one of the it was in the same group with plagioclase. It's orthoclase. It's a feldspar, a aluminum silicate, orthoclase, potassium orthoclase. Quartz, that was a non-silicate, non-ferromagnesium silicate. It was mostly silicon dioxide, very hard. So that little sand grain that gets in your shoe, yeah, you can tell that's hard, really hard. Okay? It will scratch some of these other minerals, but it won't be scratched by any below it. Topaz, if any of you have I can't remember what color is topaz. Is that the blue or the red?
Yellow.
Huh?
I think it's yellow.
Yellowish. It's the goldy ones. Yeah, that's right. Okay. Topaz is a what they call it, semi-precious stone, and it's a very hard stone. It will scratch quartz, but quartz won't scratch it. It's number 8 on the scale. Corundum. And by the way, I mentioned earlier sandpaper. If that really is sand, that's quartz. Okay, that's pretty hard. You use it to sand furniture or other things. But if you really want to do a good job of sanding, get some with corundum on it. That's 9. That's 2 above that. And if you want to cut anything that is really expensive, diamond is the hardest naturally occurring mineral. Same type stuff that soot is, which is not hard at all. Okay. Now sometimes they use other common objects for comparison rather than the actual test mineral. For example, I just used the fingernail is in between gypsum and calcite. It won't scratch calcite, but it would scratch gypsum. A copper penny is about 3.5. That's in between calcite and fluoride. I don't have a lot of calcite on hand, but I got a lot of pennies on hand. Okay, unfortunately. Okay. Glass is usually 5 to 6. Not really as hard as quartz because of the process it went through, but it's usually between apatite and orthoclase, so it's fairly hard. A pocket knife blade, which is usually some type of steel, is again between 5 and 6. Your quartz, you can sand with sandpaper your blade, and you can actually sharpen your blade with it. But corundum is probably better for that. And diamond certainly would sharpen anything. It doesn't groove it too badly. Okay. And there your Mohs hardness scale is on page 441. There's a concept supplied at the bottom of that page or somewhere there about in your book, and it says grow your own. They're talking about crystals though. Okay, so never mind. There. Okay. We wouldn't think of that. Okay. Let's look at some more of those physical properties. We had color, we had streak, and we had hardness. Here's another one, the crystal form. Okay, now most of the time we're not going to do much with that. You have to have a good magnifying glass or microscope or something. It's related to those internal geometric arrangements of the atoms, 6 basic groups we talked about. We're not going to do any more with that, but they're out there. You saw that some of the big crystals you might see, you can tell which one they are. Most of the time you can't. Okay, cleavage. Okay, no, get out of that. Get out of the gutters, man. Okay, what this is talking about is the tendency of minerals to break along smooth planes. And you've seen that in these pictures already. Look at that. You can tell. Here is what they call a cleavage plane. Nice, smooth plane. There's one there, there's one there, there's one there, there's one there, one right there and here, and really smooth plane there. A little bit less so in some of these places. Some of the crystals are very small, and you can't really detect the plane without a magnifying glass, but they do. This is exactly what a diamond cutter does. He or she studies that diamond, and then with something, real special tools, if he hits it just right, he can break off and make a perfect facet there. And that's what they want to do. Of course, if you hit it wrong, you could destroy a very valuable piece of diamond. Now, if you have a lot of dust, you can put on a saw blade and cut through concrete or something. But that's what we mean by cleavage. Cleavage is the tendency of minerals to break along those smooth planes, and you call those the cleavage plane. Cleave meaning to cut. Okay. Fracture is kind of the other side of the coin. If it doesn't break along smooth planes, it could irregularly be broken into broken surfaces. Okay? So in other words, if something doesn't cleave well, it probably fractures easily. So those are the opposite sides of the same coin. Now, another thing, and I wish I'd have said this back when they were talking about color, is luster. It's the surface sheen that a mineral would have. And here's three of them. Metallic. Okay, now you've seen some of the car colors, haven't you? It's a metallic blue. It's kind of have little flaky look to it, you know. Metallic. Okay? Pearly would be like a pearl, a milky kind of color. Vitreous basically means in vitro, meaning in glass. It would be a glassy type of surface. So it's a surface sheen. Those are three of them. I think you'll run into some others when you do the next lab. And then we have one called density. Now, when we do the next lab, we'll do density in the other column. That's a very important one. And why they didn't include it on the lab, we don't know, so I have you put it in the other column. What a density is, all density in anything, whether you're talking about minerals or what, is a mass to volume ratio. Typical units for density, grams per cubic centimeter, kilograms per cubic meter, pounds per cubic inch, or pounds per cubic foot, something like that. That's density. You could be talking about a liquid of that, a solid of that, a load of concrete, anything that you would have density as mass per unit volume. Okay. Now, sometimes they'll refer to density. If they do, they'll always have units. Grams per cubic centimeter. Okay? However, now and then you'll see specific gravity. That's a ratio of the mineral density that we calculated here to the density of water. Does anyone happen to know what the density of water is? 1 gram per cubic centimeter. Why is that true? Because when they determined in the metric system what a meter was, okay, actually they didn't do this, but it's that's about a meter from your tip of your finger to your other ear. It's about a meter, depending on how long your arms are. About the distance of a doorknob to the floor on most common doors. That's about a meter. When they were determining that, though, they weren't using body parts or anything else. The French had such problems with different parts of the country trying to cheat other parts when they were selling and buying their goods that they couldn't keep a standard, okay? So they came up with this standard and said, it's 1/10,000,000th of the distance from the North Pole to the equator, that line that passes through Paris. Now, how they measured that, I don't know. But they used that, and that standard length was a meter, and said everybody has a meter. Well, then they broke a meter into 10 units, which were called decimeters, and then broke those into 10 units, which are called centimeters. Now, the centimeter is about the thickness of your width of your little fingernail. Now, that's not what they base it on, but that's about what it is. A centimeter, width of your little fingernail. Okay? And a very common then way to talk about a small volume would be a cubic centimeter. 1 centimeter high, 1 centimeter deep, 1 centimeter. That would be a cubic centimeter. One of those little bitty sugar cubes that don't sweeten anything, that would be a cubic centimeter. Okay? So, how much mass was in that? Well, the most common material on the planet was water. So they said, what if you had 1 cubic centimeter of water? We'll use that as a mass unit. We'll call that a gram. So therefore, since they use that to name it, it is exactly 1 gram per cubic centimeter, by definition. So, if you take the density in grams per cubic centimeter, divided by 1 gram per cubic centimeter, you have specific gravity. It's precisely the same number, but without units. So if you have the units, that's density. If you don't have the units, that's specific gravity. Okay? Now, 2 factors make up the density of a material. There are others, but these are the 2 major ones. The kinds of atoms. We've already mentioned, if you have a lot of iron atoms in a mineral, it's going to be a pretty dense mineral, because iron is way up here in the periodic table. Of all the things we were looking at, iron is down here at number 26. Its atomic mass is 57. Okay? Oh, 56, sorry about that. Okay? if you look at most of the other things, of course we talked about nickel, but that's one of the heavy metals, and all those others are down there. But talking about all the other stuff, calcium is over here at 20, mass of 40. Potassium over here at 19, mass of 39. Sodium, magnesium. These are all the lightweight stuff. Silicon, carbon, oxygen, fluorine, chlorine. They're all the lightweight stuff. So iron is one of the denser materials. So if it has a lot of iron content, then that's going to be a denser material. But not just that. Remember our crystal structure? Some crystal structure may be a loose crystal, meaning the atoms are pretty far apart, and others may be really tightly placed. The packing of the atoms in the crystal lattice. There is one material, now this is not a common one, but just one that comes to mind. It is an element, and the name of that element is osmium. It's down here at 76, 190 is its atomic mass. Pretty heavy thing. But osmium, in the nature that it existed, where it exists in nature, I'll see if I can't hold it against that because it's flexible. Okay, osmium is there, but if you have osmium in nature, it's denser than gold, denser than mercury, denser than lead, denser than bismuth, but these are heavier. Why? Because the osmium molecules are packed in there much tighter than even gold or those others. So the packing of the atoms in the crystal structure also contributes to density. What makes up the atoms, if that's a heavy atom, it's going to be a dense material. Also if it's really tightly packed. So those are the major physical properties. Now we have just gone over our 3 o'clock magic time. So let me go on and mark the roll again. Brendan is still here. Brianna's still here. We haven't seen Dalen. I don't know. Does anyone know if he's coming back? He was here the first few days, but hasn't been here since. Darius is still here. Emmanuel is still there. Tara is still here. And Coco didn't make it in at all today. Okay. Bianca's still here. James is still here. Josh is still here. Gary's still here. And Carl, I'm sorry I missed Carl earlier. Carl has not made it in today. Denisha's still here. I see your hair. Okay. Shelby's still here. Brittany is still here. And Carrie is still here. Carrie. Okay. All right. So that pretty much, I think, wraps up the physical properties of our minerals. And that basically is going to be the next lab, folks, is the physical properties of minerals. Oh, wait, here's some more physical properties. Sorry about that. Here it is. This is that sheet of mica, and they're tearing off a piece of it. Oh, I'm sorry. I think they're scratching. No, this is gypsum. This is a chunk of gypsum. Most of the time it doesn't quite look like that, but that's a pretty nice piece. Hardness of 2, so your fingernail does make scratches in it pretty easily. Down here we have quartz. See these hexagonal crystals sticking out there? It has a hardness of 7, so hard that even a metal file will not scratch it. Okay? You can take a metal file that you could sand wood with, or cut through a screw or a nail or something with. Do it on the quartz, not going to damage. Okay, pretty amazing stuff. Over there, turn my page. All right. So we move to the last section under minerals. This is 17.3, mineral forming processes. This is some pretty important stuff here. Sorry, I'm going on and on and on. Now, I guess what we could do, and I sort of hate to start doing this. No, we probably don't have time. But what we'll do, especially if we finish today, which I think we will, let's just plan to have our lab the first 2 hours of the next class, unless, of course, we go to the planetarium. That way we'll be in this room, we can use the computers, and we can do the lab, because it's mostly a computer-driven lab. So you want to plan for that next time? The lab we'll do in here the first 2 hours, then we'll move to the classroom and have the rest of the class. Which reminds me, I guess we ought to move to the other room, because the other class will be coming in here at 4, and some of the students may start coming earlier. So let's go. I just called the roll, so let's take this as an opportunity to break and go to the other room. And you can take a little bit. Yeah.
What's the zip code?
What's that?
The zip code.
My zip code or here?
Zip code.
I've got it on. Sorry. Okay. Let me. Okay. If I could get you to pull that right there, thank you. All right. Hold it and crack it. I forgot that. All right, we're recording again, and I'm right into the glare, so let me move over here slightly. I know the light's coming in. Can y'all see it okay? Okay. We talked about the physical properties of minerals. Now we're looking at the mineral formation processes, okay? How did these minerals come about, okay? And this is some pretty important stuff. If I were to guess, and I'm just making a wild guess here, that a fair number of the test questions are on these kind of things, because this is really, there's plenty on the other stuff too, but there's a fair amount here too. Now, a lot of the minerals form one of two ways, and both of these ways were liquid environment. Anyone think of what that might be? Second? Okay, something dissolved in water, and you've probably seen this happen before. Have you ever put the pot on that you're going to cook your beans in and put your salt in there, and it's all dissolved, of course, and then and then you went off and got messing with something else and forgot to come back and put your beans on once the water started boiling. And when you got back, all the water had boiled away, and there were little salt crystals. Oh, it happened, huh? Salt crystals at the bottom. Well, you just formed some minerals. You dissolved the salt to begin with, but then they recrystallized once you boiled the water away. Well, that happens a lot in the earth, okay? Have any of you ever been to Yellowstone? If you haven't, try to make it a plan to go sometime during your life. You know, when you get rich and famous, make a trip to it. And you don't have to be that famous. Make a trip to Yellowstone. It is, I think, the most amazing geographical, geological set of land anywhere on the planet. There are a few places that have geysers, almost as good as that, have some of the other things, but none concentrated in a small area as Yellowstone. It's just fascinating. And when you go there, there are The geysers, of course, are there, and usually where the geysers are, there are little mounds around them because that water that comes up is hot usually, dissolving stuff as it comes, and then blows up and then cools off, and you form these mounds around them. That is a water process. That is a mineral forming process. So yes, water solutions is one. Crystals form from highly concentrated ions. What do we mean highly concentrated ions? You put the salt in the water, the water evaporated away, and then after a while you just had the crystals. So as the water evaporates away, the concentration of ions gets more and more and more. Finally, when it reaches high enough concentration, it starts forming crystals. So, and that's what happens at the geysers. It's what happens all over the place. Crystals form from those highly concentrated ions. That's one liquid solution. The other is when the rock itself is liquid. And that's what we mean by magma. Magma. Molten, think of this as melted, just change that to an E and that to a D. Melted rock. Molten rock from which the crystals can then, the minerals then recrystallize. And that's your volcanic activity and that kind of stuff. Okay? It can happen below the Earth's surface or above the Earth's surface. If it's below the Earth's surface, we call those minerals intrusive minerals. Okay, I have to get my ins and outs right. If it's above the Earth's surface, we call them extrusive. Okay? Intrusive if it cooled below, extrusive if it cooled above. So let's say that molten rock, you have a volcanic eruption. Okay? Now, some of that molten volcanic material there may plate out on the side still underneath, and if it hardens under there, intrusive. If it makes its way to the surface, erupts, now it's solidifying extrusively, okay? That could be above the Earth's surface. Now, magma is when it's a liquid beneath the surface. Lava is what we call magma that's above, that's made it out to the Earth's surface. So both magma and lava are liquid. Magma is when it's still below. Lava is when it's made it to the surface. Okay? So most of the lava is going to form extrusively crystallized rock, and the magma, when it cools, if it does cool beneath the surface, is intrusively. Okay, so we'll get to that a little bit later. I wanted to introduce the terms now. Now, some important factors in both of these processes. Temperature. Certainly that's important here, okay? In magma, to be molten rock, it has to be hot, really, really hot. So that's coming from way deep in the Earth, not in the crust, beneath the crust, coming up through the crust and making its way to the surface, okay? But even in the water solutions, when it's high temperature, and y'all realize this, I don't know if you know it, what's the relationship between temperature and concentration of ions? Is there a relationship? Okay. Any of you ever made iced tea? Okay. Now, you're from the South. Have you made sweet tea? All right, good. Okay. Now, which is easier to sweeten? Hot tea or cold tea? Hot, by far. You can get a higher concentration of minerals in a hot liquid than you can in a cold liquid, right? The sugar will dissolve better and faster and more completely in a hot liquid, and all the other minerals do too. So the temperature is important both in water and magma. Water, the higher the temperature, the more minerals you can dissolve, and then once it cools, the concentration increases big time. Okay? Pressure. Certainly, it's important in the magma. That's what forces the magma to the surface. Pressure down below and breaking the surface somewhere up here, there it comes. Same thing is happening with, in some senses, with Old Faithful and the geysers and stuff like that too. Okay? So pressure is important in both of those. And here's another thing. I think I mentioned this sort of before. Let the door close. I know I'm bothering people up and down the halls. Okay. I've mentioned this sort of in passing before, that when we're talking about carbon, forming diamonds. We talked about it some with some of the other, I don't remember where, but somewhere I've mentioned the pressure before too. If you have a lot of pressure, yeah, I know when we're talking about the Earth's core, right? The outer part of the core is liquid. It's so hot, it's liquefied. That's where that molten, some of that molten stuff comes from, okay? But even deeper, the inner part of the core, even though it's even hotter, the pressure is such it forces it back into a solid structure, okay? So the pressure makes a lot of difference too. We'll see this when we get to the rocks part. We're still in the mineral parts, but it is important. Time, a big thing. When we're talking about diamonds, I mentioned the high pressure, I mentioned the high temperature. What I failed to mention was the time it takes to make a diamond. It takes that pressure, that temperature for a long period of time. You've got to change the bonding, the chemical bonding of those molecule atoms together, or molecules, and that's what changes some of the structure, changes the mineral structures, okay? Now, availability and concentration of ions in solution. This is mostly talking about water solution, but in some senses about the magma solutions as well, okay? What types of crystals you're going to form depends on what's in there to begin with. Of course, you're not going to make much gypsum if you don't have much calcium and sulfur in there. You've got to have both of them, sulfate, okay? Now, and this is where we talked before, glass. Glass is not, goodness gracious. Oh, I guess this is a really shaky board. I mean, I didn't know I could do that to it. Okay.
We just found out that the new paper can show that.
Okay. Hey. Okay.
Good,
Yeah, I'm still far. Yeah, you can sit anywhere you feel comfortable. Okay. All right. Okay, glass is, as we mentioned before, is really not a solid. It's a rapidly cooled, they say it is a solid, rapidly cooled solid, but lacks the crystal structure. And that lack of crystal structure actually allows those molecules or atoms to move past each other. Really slowly, but they do move past each other. Ever so slightly, okay? So that's why sometimes it's just called a supercooled liquid and not really a solid, but this is still calling it a solid. That looks like a solid, feels like a solid, it is, but it doesn't have that crystal structure, okay? Sorry, I'm trying not to. All right, so let's look at minerals formed at really high temperatures, okay? This is talking mostly about the magma formed minerals. Molten rock cooling to become crystals, minerals, okay? And the guys who came up with this thing was a guy named Bowen. Could be a paper topic right there. Or how did he develop this Bowen reaction series? Or applications of it. Several things you can write on there. All right, what this is, now we're talking about the silicates now. How much of the Earth's crust is silicates? 92% are silicates. The rest are non-silicates, okay? Now, in those silicates, there's two major classifications, really three, but the two major ones are basically high iron. High iron? No. Ferromagnesium silicates and the non-ferromagnesium silicates. Okay, pretty clear classification, right? And then the third one is the clay crystals. Yeah. So we're not talking about those here. We're talking about those that are formed from at high temperatures. And this is Bowen's saying. We're talking only about the silicates, not the non-silicates. The ferromagnesium silicates crystallize at a higher temperature. In other words, they come out of solution, out of that magma solution at a higher temperature, and then the non-ferromagnesium magnetic, I prefer magnesium silicates, come out at the lower temperatures, at the cooler temperatures. So they'll stay in solution a little bit longer. Okay? The minerals crystallizing later, okay, fine, okay. The minerals crystallizing later are progressively richer in silicon because the ones that crystallize early at the hotter temperatures, the irons come out then and the silicons come out later. So guess what? The darker ones are deeper, the lighter ones are shallower, generally. The crust is mostly silicon and oxygen. How much of the Earth's crust is silicate? 92% or something. Yeah, it's amazing. Okay, so those later will be. Now here's this Bowen reaction series, and it will see some of the same things we saw before. Okay, this side is mostly your ferromagnesium silicates. The first out of solution at the highest temperatures are your olivines, okay? Usually really high iron content, okay? Next is the augite. Quite a bit of that is our iron ore, augite. Next out of that is hornblende. Now notice what they did with this. They also made the color darker here, lighter here. The further down here you get, the lower the iron content. So it gets a little bit lighter in color. And then finally the biotypes, most of the iron compounds, iron silicates, ferromagnesium silicates that you find nearer the surface would be more of your biotype. Okay. Now this side over here, they've colored similar to that, okay? And they have the relative temperatures as similar to this, but these are your non-ferromagnesium silicates. In reality, these are should be down here, kind of. It's not suggesting they come out at the same temperature as here. It's just this is a non-ferromagnesium silicates on this side. So what's the order of the non-ferromagnesium silicates? Well, your plagioclase feldspars. Can anyone tell me what a feldspar is? It's non-iron, so it's non-ferromagnesium. What would be the metal in the feldspars? Aluminum silicates. These are aluminum silicates. The plagioclase are your calcium aluminum sulfates, silicates, down to your sodium aluminum silicates. Okay? Those are your plagioclase feldspars. All the feldspars are pretty much aluminum. Okay? Aluminum silicates. Then you have your potassium feldspar. It had its own name. You remember what that was? It wasn't plagioclase, but it was orthoclase. That's your potassium feldspar. That comes out at the coolest temperatures. These come out at the higher temperatures, down to sodium at cooler, and then finally potassium feldspars there. Then, after that, is the muscovites at even cooler temperatures. Remember what that was mostly? Potassium. Now, this has potassium silicates here. This is potassium aluminum silicates. This is just potassium silicates, okay, muscovites. And then the quartz, mostly just silicate. That's all, silica. Not much else mixed with it. They are the last things to come out. They stay in solution, the magma solution, the longest. They have the lightest color. The muscovites are pretty whitish. These are almost clear. I mean, hardly any color at all. These are lighter colors. And you go up here, you get into your brown. I think these are pinks, the potassium feldspars. The sodium, they get into tans and browns and stuff. Over there, it's mostly blacks. Grayish and darker until it's black. Okay? Quartz, almost no color at all. The last thing out of solution is your quartz, which is just silica. Silicon dioxide, basically. Okay, makes sense? This is your silicate minerals formed at higher temperatures and then cooler as you go. This is still pretty hot by the time the quartz comes out. Okay, still pretty hot. Now, what about those minerals formed at normal temperatures? Those, remember, are hot, high temperature, still probably down deep in the Earth's crust. So these formed in the Earth's surface, where the temperatures are much cooler, normal temperatures, in contact with oxygen, in contact with carbon dioxide, and in contact with water. Now, why do they mention those things specifically? Now, these may be other minerals too. These may form oxides, carbonates, hydroxides. Other things as well, but these, when these are formed at the surface, you get these other things mixed in. And here we have carbonates. They don't have a thing here for sulfates. Oxides, halides, those are other things, your group 7, and sulfides, which are your things below oxygen. Okay. Now, except for the oxides, except for this, these have substantially lower hardnesses and lower specific gravities than minerals formed at high temperatures. High temperatures, usually deeper, cooling more slowly, the crystal structure forms pretty tightly and stuff. When these form fairly quickly at the Earth's surface, it's usually, these are lightweight materials, oxygen, carbon dioxide, water, lightweight materials, so these typically are going to be lighter weight and less hardness, except for the oxides. Some of the oxides can be very dense, like iron oxide, and can also be very hard. So that's sort of the same thing. Yeah. Dense, meaning high specific gravities, and harder. So the oxides typically are pretty hard, even formed at the surface. For instance, I'm not absolutely sure this is the same case, but do you remember there was one time a soap called lava? I don't know if any of you remember that. Basically, it had in it pumice, which was basically finely ground lava dust, you might think of. Pretty hard stuff. In fact, my wife found somewhere, I don't know where she found it, these scouring sticks, which are made of pumice, meaning they got volcanic stuff in them. Very small particle size because they formed at the surface, but still very hard. And boy, those scouring sticks, you can clean rusted metal, you can clean all sorts of things with those. I don't know exactly what goes in them, but they say it has pumice, which is volcanic type material. Still pretty hard if it has the oxides. Okay, now we have other mineral issues. Oh, I didn't ask. Did you have the other slide? Okay. The other one, the previous one? Okay. I get to talking and I'll get carried away. Okay. We also have altered minerals. Now, what do we mean by that? These are minerals that have been exposed to different environmental pressures, temperatures, chemical solutions that actually changed one mineral into another mineral. Now, later when we talk about the rocks, we will see some very specific examples of this, okay? Now, this is usually happening at 150 degrees Celsius, which is 50 degrees above the boiling point of water, so that's fairly hot. Up to about 2,000 atmospheres of pressure, that is a lot of pressure. How much pressure are we under right now? 1 atmosphere of pressure, the weight of the atmosphere above us. Now, this is just an example. If you go into the ocean and go down about 10 meters, that's about 30 feet, about 10 yards down. That's not all that far, right? Okay, a little more than 10 yards down. You now have another atmosphere of pressure over you. Our whole atmosphere above us is about like a column of 10 meters of water. So, to get to 2,000, really deep in water, but you wouldn't have to be that deep under rock and stuff, but usually under huge amounts of pressure, okay? And usually really high temperatures. And here are some, I don't know if you'll recognize some of these. Garnet is one of those semi-precious stones. What's that, a greenish color? I don't know what stones are.
Like a peach color.
A peach color? Is that right? Okay. Okay. Epidote, I don't even know what that is. It sounds nice, but talc, which is that very soft mineral, but it forms under, is altered at very high temperatures and pressure. Graphite, we talked about that. That's a carbon mineral that's real slick as opposed to abrasive like diamond. And serpentine, one of those asbestos sources that we are not very favorable anymore. Actually, one of the areas they did a lot of asbestos mining back before it was a bad thing was in, I think, southwest Georgia, so not too far from the Alabama side over in Georgia. They had a lot of naturally occurring serpentine, and they made their asbestos from that, and now they don't anymore, okay, because it's now a bad news. Even though he's smiling about it, we don't. Okay, good deal. Got it?
Got it.
Okay. Now let's look at some of the ore minerals. Where were the ore minerals classified? Okay, naturally occurring, and they were over with the, one of those 8, they were number 8, non-silicate minerals. Remember, your silicate minerals were over there. They were the ferromagnesium, non-ferromagnesium, and clay minerals. Then the non-silicate, there were 8 groups of those. The most abundant were the carbonates. Then you had the, lots of other sulfates and the oxides and those. But the very last one down there, non-ferromagnesium, were your ores, your naturally occurring minerals. Mineral deposits with an economic value. Now, what makes them valuable economically? Okay, precious is what makes them precious. Okay, quite often it's their appearance, including color and things like this, and maybe things like diamond, the hardness and stuff like that. But quite often it's how rare they are, okay? But also how pretty they are, like gold and silver and copper, but also how rare they are. Those are all platinum. It's kind of dull looking, but it's the other thing is what uses it has. And some things that probably were not considered very valuable, and sometime later said, hey, this is pretty valuable stuff, once we were able to use it for something else. Like copper, I don't know if they had much need for it until we had electricity, and then suddenly, hey, this is good stuff to have. Of course, it was used for bronze and brass and things like that. Its color was pretty nice too. Okay, now these ore minerals are mineral deposits with economic value, either because of how rare it is, or how pure it is, or how, whatever, uses that it has. Often found in veins, meaning other rocks would be surrounding it, and they would extract just the ore, okay? Now these veins are thin, flat bodies of mineral material, like it would form between layers, and that's what they would call veins, left over from crystallizing magma and flushed away in hot water solutions, okay? Have y'all ever read much about how they purify, say, things like iron or copper or other things? What they usually do is heat it very hot, right? Melt it, and then the impurities will sometimes float to the surface, and they skim those off. It's called the dross sometimes, okay? And then they let it cool slowly, and the different things will come out, just like Bowen series will come out at different temperatures. And I think gold is one that comes out at one of the highest temperatures. I don't know I can't remember all that. But you see, if that's occurring in nature, and certain things are coming out at different temperatures, then it would make sense that once the temperature got to a certain thing, then a bunch of this would all come out at the same time, then other stuff comes out later, and that's why it would be in veins, in layers, okay? Because they reach that temperature at about the same time. So that's why it's left over from crystallizing magma, and then also sometimes flushed away in hot water solutions. If it's more soluble or the other stuff is more soluble, it's washed out. Now here's the other: pyrite, iron sulfide, fool's gold, chalcopyrite, You would think that's calcium, it's not. It's a sulfide of copper and iron, a mixture. So the calco means copper. Where the cal comes from, I don't know. And then the pyrite is iron sulfide. Now, to me, this slide has a lot of words left out. That's why reading the book is really, really important. Can't go into all that. In fact, I'm not even sure the book goes into it that well, but it sure does more than the slide does. Okay? That ends basically the first half of the chapter. Remember, this chapter was rocks and minerals, but we covered them in reverse order, minerals and then rocks. So now we're into the rocky part. The hard rock cafe, no, that's something else. Okay. So in the rocks, what is a rock? That stone that's there in the driveway or something? Well, maybe. It's an aggregation of one or more minerals, perhaps other materials as well. So a rock usually is a mixture of several things. That's what aggregation means. It may be mostly the same material, like that grain of sand that's been in your shoe and bothering you all that time. That may be mostly quartz. And if it's mostly quartz, that's just one mineral. But it could be, pick up any old rock, piece of gravel out there. Look at it, you'll see a little bit of quartzy looking stuff, you'll see some dark stuff, you'll see other colors. That's a rock made out of several, perhaps several minerals, and maybe even some non-mineral stuff. Now, what is it to be non-mineral? Maybe organic type stuff. Maybe bone fragments or shell fragments or something like that got pressed in and became part of the rock, but it's not really mineral. Or a glassy type material that's not crystalline, but it's mixed in there as well. Okay, so a rock could contain other stuff that minerals. Remember, mineral had a definition that was very restricted. So minerals are physically combined to make rocks. And by the way, when they say physically combined, we'll talk about this a little bit later too. Sometimes you have what they call a cementing agent. That's a sort of like a glue. It's a naturally occurring glue that's holding these various components together. And that may not be itself a mineral, but it's very much a part of the rock. Okay? So they are physically combined to make rocks. Okay? So most rocks will have a variety of minerals in them. We'll see some that are a bit more pure than others. Most rocks, guess what? Are silicate minerals. Why would that be? 92% of the Earth's crust is silicate, so most rocks are going to have silicates in them. No way around it, or very little way around it anyway. So what's your classification scheme? We got to classify rocks as well. They're based on how the rocks were formed. We had mineral forming processes. Now what are the rock forming processes? Three main categories. And someone mentioned it already today. I think you did. Igneous rocks. Okay, we'll name what that is. Second, sedimentary rocks. I think someone mentioned that today too. Okay? And then I think I may have mentioned metamorphic rocks. Okay? So those are the three main groups. Okay? We're going to hit each one of them separately. That's why I didn't give a full definition there. Let's start with good old igneous rocks. What word do you almost see the beginning of there? Ignition, exactly. What does that mean? Fire, to ignite, to catch on fire. Well, these don't really catch on fire, but these are formed from magma, liquid rock, molten rock, and this could be formed either above the surface or below the surface. And this is where I was talking as if they were minerals. I was really talking about rocks, but that's why I wanted to mention it, intrusive, extrusive, whether it's under the Earth's surface, intrusive, above the Earth's surface, extrusive. Okay? So where were the rocks? Okay, they're formed from magma, from hot rock, fiery rocks, melted rock, hot. Okay? either above or below the Earth's surface. So here's a subclassification of igneous rock: intrusive, extrusive. Okay. Catch this statement. All rocks were at one time igneous rock. Okay? Because guess what? How was this Earth formed? Probably as a fireball, as the sun was exploding and doing things. We were probably pretty hot and molten completely. So everything here was at one time. I mean, all the rock were one time, usually not that long ago, igneous rock. Okay? That means all sedimentary rock probably have some igneous rock in them. They at one time were. All metamorphic rock were at one time made up of igneous rock. Okay? We'll talk about that later. Now, we talked about where they are formed, above or below the Earth's surface. We'll get to that over here. But the other thing is the rate at which they were formed, the cooling rate. That determines the texture. Okay? Now, are these exclusive of each other? Not really. Because usually the things formed way below the Earth's surface are going to cool very slowly. So that is going to affect the texture as well as the type of rock. And usually the things that were formed cooled at or above the Earth's surface, those are going to usually cool a bit more quickly, which are going to be fine rocks. So let's look at the combination of those two together, where they were formed and the cooling rate. Intrusive, interior, that's intrusive interior, below the surface, formed beneath the surface. These are igneous rock made from molten rock, but they cooled beneath the surface. Slow cooling processes, and those slow cooling processes produce large crystal size. I hope that sort of makes sense. If that magma is cooling slowly, then the crystals grow slowly, and it builds on the same crystal and can get quite large. And if you remember some of those pictures of that quartz, those crystals are big-looking crystals. So even though quartz was at the lowest temperature, that still had to be a very slow process. Okay? Now, the slow cooling produces larger crystals. The larger crystals give you a coarser grain. Okay? Because you have bigger crystals in there. Okay? So, where it was formed also interacts with how rapidly it cooled, or how slowly it cooled, and that influences the crystal size, which of course influences the texture. So you see 4 things here that are all interrelated. On the other hand, extrusive igneous rock, that's rock that formed from magma, but cooled above the Earth's surface, above the Earth's surface, extrusive, exterior, formed from lava, not magma. Why? Magma is liquid rock below the surface, lava is on the or above the surface. So that would be from lava, not from magma. Okay? So that's what it was formed from, where it was formed, and of course that's going to produce a rapid cooling process, which will be smaller crystals, which will be finer texture. Okay? So all those form together. Now, in addition to that, we also have the extrusive igneous rock that may have formed so rapidly that it didn't crystallize at all, or very low crystallization. That's going to form your glass. Here is a picture of granite, one of the most common igneous rocks. What can you tell me about the color of that granite? It's stony looking, but what's the color? It's light colored. What would that indicate? Not much iron content. This is mostly from non-ferromagnesium minerals. Mostly quartzy type materials, especially where it's zero white. Now you see some dark areas in there. This can have some minerals in it, maybe biotite or something else. Very small, not small crystals, but crystals of that, which are a little bit darker. So this is a mixture of more than one mineral, more than likely. but that makes granite. And you want it to have a little bit. If you want your countertops, some people like the pure same color, but most of the time you like that little color stuff in it. So that's why granite's pretty popular. Pretty hard rock too. A coarse grained, what does that tell you? When you hear it's coarse grained, what does that tell you?
It's got silicate.
It's what?
It's got silicate in it.
Okay. All of these have silicate in them pretty much.
It
The
cooled
igneous rock.
slowly.
Second?
It cooled slowly.
It cools slowly, forming
Large
larger crystals. So yeah, coarse grain tells you cool slowly, which probably means it's intrusive igneous rock. So you see, just that one word will tell you a lot about it. Coarse grain, large crystal size, cool slowly, probably intrusive igneous rock. Okay? Composed mostly of light-colored, light-density, non-ferromagnesium minerals. Okay? Now, some of these may have a little bit darker color, but some of that may be a few ferromagnesium minerals, but not many. The Earth's continental crust is dominated by granite. The Earth's continental crust dominated by granite. Okay? And by rocks with the same mineral composition as granite. So it may be others with similar mineral concentration. Now this here, this is what we're talking about, Game of Thrones folks. This is a piece of obsidian, which has the same chemical composition of granite. Does it look like granite? Nowhere close, okay? The obsidian has a different texture because it does not have crystals. It cools so rapidly that the crystal structure didn't come about, and it is a glass, okay? And it looks glassy, okay? The curved fractured surface is common in non-crystalline substances such as glass. And if you've ever seen glass break, and of course most of you have, it does break sort of in curves quite often. Now my wife likes to do, she's a professor at UAB, but she likes to do in her spare time stained glass. You mentioned that, Brittany did. And she really does some good stuff, but boy, she can get really frustrated with that glass because she's trying to break it into the shape that she wants it in, and it'll just take off and make these curves in places she doesn't want it to do, and she has to throw that piece away and do another one. That stuff isn't cheap, by the way, okay? So, but she makes a lot of money, so she doesn't care. Okay, and I don't cost that much. Okay, so we get a lot about the igneous rocks by where they formed, how rapidly they cooled, or how slowly they cooled. Lots of things come out of that. So let's continue looking at that igneous rock classification. Two factors that go to that classification. What's the mineral composition? Is it ferromagnesium? Non-ferromagnesium. Ferromagnesium would be what? What would be some characteristics of that? High ferromagnesium. The dark color. The dark, usually blackish coloring. If exposed to air a lot, it could rust some and look reddish, but yeah. And the texture, what would be the coming out of the texture? Why would the texture be what it is? The what? I can't hear you. Okay, the hardness is a part of it. What we mean by texture is how large the crystals are. And what does that depend on?
It would probably be small, I would think.
What would be small?
The first one.
The ones cooled at the surface would be small because they cool rapidly. So the cooling rate, if it's cooled rapidly, small crystals cool slowly, large crystal, coarse texture, small crystal, fine texture. Okay? Now, the non-ferrous composition, okay, they need the figure here. Let's get the figure. This is a pretty complicated looking figure, but not too bad. Okay? Now, by and large, these are all silicates. Well, yeah, all silicates. The coarse grained at the top, what causes that? Coarse grain? The what? Large crystal size. What influences that? And I think you said it. The cooling rate. Is that what you said? Okay, the cooling rate. The large crystals cool slowly. The small crystals, fine grain, cool rapidly. So here are the coarse grain: granite, diorite, gabbro. Okay? Coarse grain, large crystal size, cooled slowly. The fine grain, rhyolite, andesite, and basalt, cooled rapidly, small crystal size. Okay? Make sense? Now, what's the rest of this talking about? The non-ferrous composition is on the left of the figure. Lower iron content over here. Now, I kind of don't like this, but they do it all the time. They say CaO, FeO, and MgO, as if these are all oxides in there. They don't have to be oxides. That should be low calcium, increasing calcium, iron, and magnesium. Why didn't they say that? Why did they throw the oxides in there? Increasing, going that way, potassium and sodium. And they're not necessarily oxides. It could be chloride, just potassium and sodium content. And also, going that way is increasing silica content. That's the major thing. That's the heavy hitter here. Because the silicates make up 92% of the rocks on the Earth's surface, in the crust. Okay? So increasing silica is that way, decreasing silica this way. Increasing iron and magnesium and calcium this way, you also increase potassium and sodium that way. And if you think back about Bowen's series, the irons, the heavier ions are higher up, and the calcium's up here, then the sodium down here, and potassium at the bottom. So yeah, this is all sort of ties in there together. All right. So on your high silica side, 75% silica, silicon dioxide, you have mostly silicon dioxide, and if it's almost totally silicon dioxide, it's quartz. Now, it can have some other things in it, but that would be quartz, okay? If it has a fair amount of silicon dioxide in it, but also has others, these are some of your feldspars, which what kind of, these are it's also a silicate, but it's a aluminosilicate. Aluminum silicates are your feldspars. And these are the high potassium, and see potassium's high here, and aluminum, they don't have aluminum on here, but aluminum would be down here in that direction too. Okay, feldspars. The sodium-rich feldspars, they are, trying to see what the percentage on that scale is. I guess that's just percent of these minerals. So your sodium-rich feldspars, the potassium are further here, sodium are not as far here, but those are the sodium-rich plagioclase. I was just going to ask what that was. Sodium plagioclase, here are the calcium plagioclase. And these are just a mixture of the two, I guess. Okay, plagioclase, feldspars. So all your feldspars are aluminum silicates. And then you have your iron silicates, okay? The ferromagnesium silicates. The biotite are the lightest ones there. They have more silica in them. They're silicates, they're iron silicate, ferromagnesium silicates with more silicon in them. So they're a little bit lighter color, not as dense, that kind of stuff. Then your amphibole, which really they didn't mention that much before. Pyroxene they didn't mention, but they did mention olivine. So you see you have different names in here. So, to tell you a little story. We had our master bathroom redone. Basically what was happening, the tile that was on there, we just could not keep the grout clean. We couldn't even get it clean. We bleach it, we do everything, we could not get that grout. It just was black in between. What is going on here? My wife didn't like the tile much anyway. It was put in after the house was built many years later. It was a more modern look. She liked the older look. And so she said, I'm just tired of this. Let's see if we can have this redone. And it's a real small master bath anyway, so it wasn't going to be a huge undertaking. But we had this guy who was just really, really good with tile. And we had picked out generally pretty cheap stuff, but good looking stuff. But we go cheap, can. And but it was pretty plain too. She just wanted a tannish kind of look to it. The other had been sort of pinkish, and she didn't care for that too much. And so actually the floor, sort of big tiles like this, but they were actually a man-made material. But they had taken things like mortar and stuff like this, and chunks of, naturally occurring stuff, whatever they had, and really pressed them together, high temperatures and stuff, and man-made, a pretty hard thing. It looked sort of marbly, but you could tell it wasn't really marble. But they did not do up nicely. It was pretty good looking floor. But it was whitish looking with little tans in it. The walls were sort of tans of those tiles. But when the guy went through to take out the old tile, he said, this is what your problem was. They didn't put any sealer behind it, and there was all this moisture. That was not mold on the outside, it's mold coming from inside the wall. He said, it's good you got this out of here. He said, your floor would have probably already gone into the living room downstairs if it had not been this oak flooring that they built the bathroom on top of it. It was just really good wood. Thank you very much, old people that built the house. Now, why did I get into that? Oh, yes. So the tile guy, he thought our colors were a little too bland. We needed a little more pop to it. So he said, why don't you go, because we were buying the materials, he said, why don't you go get some black granite? And that'll give a nice contrast to it. I said, and he told me a place to go. Sure enough, I found it. And later I was talking, now this is long before I taught this course. Later I was talking with my niece, who was a geology type grad student. I think at that time was in Western Kentucky. No, Eastern Kentucky. And doing her master's. And she said something about it. I said, yeah, this is black granite. She said, there's no such thing as black granite. Well, she said, granite is, by definition, light colored. Look at this. Quartz, feldspars, what little bits, remember that other picture? Little bits of darkness it had? Biotite. High silica content, but iron, ferromagnesium, but not much of it. Usually 25% or less, down to as little as 90%, 95%, or 5%, no more than that, 2% maybe, okay? That was that little bit of black, dark streaking you saw in the granite. She said there's no such thing as black granite. By definition, black. And then within a year or so, I was teaching this course, I went, yeah, she was right, no such thing as black granite. So what was that? Well, it was and we'll see a sample of it. I brought some pieces that broke off and stuff. And we'll see that it was a very fine-grained, dark-colored basalt. Okay? That's what it was, not black granite. Of course, the tile guy, he just said, it's light granite, it's hard like granite, black granite. No such thing, it was basalt. Now, on our countertop in the house over in Georgia, they put a dark color on, and I think they actually said that was going to be basalt, but when I looked at it, big crystals. Not basalt, it's gabbro. And that same smart mouth niece, that same niece that knew what she was talking about, she said, oh, nice piece of gabbro here. Got that one right. Okay, finally, okay, but she didn't realize. Okay, it has darker colors, okay? So you see there's no such thing as black granite. And in fact, and literally, they don't have these colors too badly. I mean, they can't put this black or you couldn't read the words behind it. But these are your browns and your pinks and stuff like this, and these are almost white. So you do have some rich brown granites. Those would have quite a few plagioclases in them. Okay. So you see, granites can vary a lot. Okay, I think, did we beat that to death completely? I hope so. Okay. Now, remind me, 4:30, y'all got to stop me, right? What's going on then? Test 3, all right, I knew you wouldn't forget. All right, I think we finished with the igneous rock. What did igneous rock mean? Second?
It was made above or below ground.
Above or below ground, but what's it made from?
Lava.
Lava or magma? Magma below, lava above. Yes, it's from molten rock. That's what igneous rock. How about sedimentary rock? Where would that be coming from? Sediments. Things that fall out of solution. Here's our water base. Formed from particles or dissolved materials from previously existing rock. Now, what do we mean? Particles, I think I know what that means. Little pieces, particles, okay? So, guess what? All rock erodes. All rock breaks down. If that sand that was in your shoe, one time that was a piece of rock somewhere, okay? But it broke apart, it may have been physical. We'll talk about this in a later chapter. Some type of weathering process that broke it down. If it breaks it into particles, that forms one type of sedimentary rock, but it could also dissolve, because what is breaking that down? Quite often water is dissolving. Remember those cementing agents I talked about that hold the rock together? Maybe the water is dissolving those away. And then when you dissolve it away, the particles break off. So you could have particles or dissolved materials. Now, what's the difference between breaking something and dissolving something? Breaking is physical, and really dissolving is kind of physical, but it's also more chemical. It's like that sugar crystal. It was a hard crystal. You put it in your hot tea and it dissolved. It's still sugar, it's sweet, but it's not, you don't see the crystals anymore. It actually dissolved it. Now it's interspersed. So this is what we mean, dissolved materials. You don't see them anymore. Okay? Well, how can you be formed from a dissolved material? It recrystallized, just like that hot salt water made the salt crystals again. So it goes back through a process. So we classify this as sediments, if they're from particles. No, wait, we'll get to that. Sediments. What do we mean by sediments? Accumulations of 3 different classifications of the particles. Silt, sand, and other materials. Now, actually, there's more than 3. You could have coarser materials than sand. Remember, sand was anything up to 2 millimeters in thickness, 2 dimes together. Okay? That would be a large sand particle. Okay? Silt, remember my description of that? In other words, a sand is a small particle, but when you rub it between your fingers, it feels gritty. That's what makes it a sand. I mean, that tells you it's a sand. A silt, you rub it between your fingers and it feels like flour. You don't feel any grit in flour, do you? If so, I don't want to eat your biscuits, okay? So, okay. That would be silt size, really small. Other materials, you could be as small as clay size. Submicroscopic, 2 microns. Split that into 1,000 equal pieces, and 2 of those together would be the largest clay particle you could find. That's really small. But you could have other materials that are bigger than sand, gravel, and those have special names. We'll get into those later. Now, sediments are broken into 2 types, as set here. Classic sediments are those that are particles, particular, accumulated from rocks at various stages of breaking down. Classic means particles. Okay? Now, you're going to see this table at least twice or something like it 2 or 3 times. Okay? This is the classification scheme for your sedimentary rocks. Okay? Clastic means particles. Now, if those particles are larger than sand, say gravel pieces, okay, that's called conglomerate or breccia. Okay? That may be breccia. I've never heard anyone pronounce it, so I don't know. I call it breccia. Okay. Now, in your text, let me get over here, by the way. We're into rocks now. There was a piece of granite. I should have shown this when I was showing that other slide. The whitish colored things are probably your quartz. The brownish and even greenish kind of stuff, that's probably your plagioclase, pinkish, plagioclase, or feldspars. Let me just call it feldspars. And then the darker parts could be a little bit of biotite. Remember that previous one we had? Should have had, oh, there it is right there. It's that there. The darker pieces are the biotite, the whiter pieces are the quartz, and then the in between that, the brownish and tannish are your sodium-rich plagioclase, and your light but not whitish would be your potassium feldspars, which are aluminum silicates. Okay? Okay. Now, oh, here's something else. I should keep my book closed, but it's hard to do it here. The cost of mining mineral resources. That's a good little blurb to read. I mean, it talks about all kinds of costs. Okay? Certainly costs in mining mineral resources would be getting the land and rights to use the land. And I don't know if any of your landowners here, house owners or something, or you might be one day, you might find it interesting, even though you own the property, you may not own the mineral rights to the property. So it can be rather strange sometimes. So there's those costs. There's also the cost of how deep is the mineral. So how much do you have to dig to get down to it? How much overburden do you have to move out of the way? Then once you get to it, how pure is it? How much of it do you need to get out to make a profit? There's all sorts of costs in there. And then there's environmental costs. After you bring up this stuff from way down deep, especially those that were your sulfides, remember those, the pyrites and those kind of things? If you bring those up from way deep, then that sulfide in a chemical process changes to a sulfate. And then the process of doing that, the sulfur that didn't have any oxygen with it now gets oxygen attached to it. Where'd that oxygen come from? Probably from water, but water is H2O. So when the oxygen goes over and joins with the sulfur, this is real simple, I'm oversimplifying it here, you have hydrogens left over. Guess what that is? Acidity. Sometimes that mining spoils, that's what they call it, when they bring that stuff to the surface, you can have some very acidy soils. And sometimes nothing will grow there. And they'll erode away like crazy. And then you have silt problems, you have other things. So quite often, in fact, my wife's oldest niece married a guy whose father was a soil physicist type person, which is basically what I am, but he works for the mining companies, and he goes in and helps them reclaim the land. They have to take that overburden that they dug away, spread it back out, and ameliorate it with lime, ameliorate it with other things to get the nutrient content back up so that trees will grow, grass will grow, and it can return close to what it was before. Never make it exactly like it was before. But then you have to worry about, you got to get some of the native species back in there. You don't want to bring in fast-growing stuff, but it's not native, then you could mess up the environment. There's a bunch of costs that you don't realize. I'll let you read the blurb. It's probably well worth it. They have this picture of some obsidian there. We already talked about that. And collect your own. They're talking about minerals here again, folks. And they're doing that. Now we've got the sedimentary rocks. Okay. A new one of these finally had asterisks by it, and I wanted to get it right. What's the difference between conglomerate and breccia? They're both made out of plastic, meaning particular matter, that's larger than sand, that's mostly gravel. So what is the difference? Conglomerate has rounded fragments, so the pieces of gravel in that are rounded, probably from water or something like that, and breccia is the angular. Okay, we'll see a picture later, but I wanted to give you the difference between this is rounded, this is angular. Okay, going down smaller than gravel, clastic material of sand. Remember, sand is 2 millimeters or less, okay? And that, of course, forms sandstone. And we'll have some samples of that during or after the next lab, okay? Now, another clastic, get a little smaller particle size. This is big, sandy, now silt and clay. You could split this into silt and clay, and this forms siltstone, if it's silty particles, claystone, if it's clayey particles, or shale. Ooh, where did that come from? Shale is a layered rock that is basically, if you drive up toward Nashville, you'll see a lot of shales showing up. Things that are in layers, definitely in layers. Okay? But they're from very small. We'll talk about that a little bit later too. Now, we've only talked about clastic here. We haven't talked about chemical. That's when it's dissolved materials, formed from dissolved materials from previously existing rock. Okay? Either the rock material itself dissolved or the cementing agents dissolved, it's dissolved that then comes back out of solution again. Like those sugar crystals or soft crystals when you boil your water away. Okay? So I think I'll hold off those until we talk about the chemical. So let's move on to chemical. Well, okay, here's the other slide. What are the things larger than sand? I mentioned gravel, and you can have sedimentary rock with gravel in it. The next thing up is what they call boulders. I've never seen sedimentary rock with boulders in it. I've seen boulders with sedimentary rock in it, but no, it's just the next classification up. Anything over 10 inches in size, that's called a boulder. Anything between 0.08 of an inch to 10 inches, that's gravel. It's pretty good sized stuff. Sand, 2 millimeters, which is, and this is also 2 millimeters. 2 dimes together up to 10 inches. That's sand. That's gravel. Less than 2 dimes, that's sand. Until you get down to the floury or dusty stuff, that's silt. And then the clayey stuff, which is really, really tiny, that would be your claystone. See, the other table had a grosser classification. This is a little finer classification. And here's where they gave the breccia, conglomerate, and breccia. Okay. And some of your siltstones and claystones are sometimes called mudstones, shale if it splits along parallel planes. Okay. Now, I don't know this for a fact, but it's my suspicion. There was a company that made, probably still do, wood stoves. And there's one type of rock that they made the wood stoves from was called soapstone. And it actually almost has a slick kind of feel to it, as if it was soapy, okay? It's not really soap. My guess that's some of this, what they're calling mudstone here, or maybe claystone. There, it could be siltstone, very, very, very fine particle size, okay? But that would probably be a sedimentary rock from that, okay? So there's that slide, or one very similar to it. Now, the chemical sediments. The chemical sediments are from dissolved rock materials, not pieces, dissolved, in solution. You don't see it anymore, but it's still the same material. Okay? There are 3 sedimentation paths that happen. And we'll see sort of some of the examples of this. The first thing that happens is the chemical precipitates out of the solution. Now, what does that word precipitation mean to you? Yeah, okay, we think of it as rain. Really, the better definition of precipitate is something that falls, like rain. But this is out of a solution. Now, I don't know if you've ever done a chemistry lab before, but I remember the first chemistry lab I did when I was in college. They gave us some silver nitrate, which was dissolved in a solution, it's soluble, and they added to that some calcium chloride. Well, silver nitrate was soluble, but silver chloride was not. And as soon as you put the calcium chloride in with the silver nitrate, and it was all solution, suddenly you saw a white powder falling out. That was a precipitate, okay? Something that comes out of solution. It was in solution, now it comes out. So that's what we mean by chemical precipitation. Maybe another ion comes along in solution that replaces the one, and then what its co-ion was, they don't dissolve anymore, so they come out of solution. That would be chemical precipitation. Another thing that could happen is crystallization from evaporating water. That's like you leave the pot on the stove too long, it boils away and the salt is left, okay? It crystallizes from evaporating water. And it doesn't have to be boiling water, it's just water that evaporates, okay? Now remember, that hot water will hold a lot more solution, a lot more sugar, a lot more salt than the cold water, right? So down there, when it's down like the geysers and stuff down there, really hot environment, it can dissolve a lot of stuff there. But then it comes up to the surface and now it can't hold that in solution, so now the water evaporates away and the pieces of the rock that's dissolved before, now they recrystallize as the water leaves. And then your last one was biological sediments, okay? Remember, rocks can have non-mineral pieces, such as little pieces of shell. A lot of limestone, sometimes you'll see little pieces of shell in it. They formed at the bottom of the ocean. It had pieces of biological sediments also coming out and being part of the sedimentation. Okay, let's see. Let me get the other half of the slide here. Here are the chemical. We've already talked about the clastic. Here are the chemical sediments. When you have calcium carbonate dissolved in the water, or calcite dissolved in the water, that forms limestone when it comes out. Okay. Now remember, limestone is probably going to have some silicates in it too. Calcite is non-silicate, but remember the stone can have mixtures of other things. So it may have some, and it usually does. Dolomite is when you have not just calcium carbonate, but calcium and potassium carbonate. Gypsum comes out when you have calcium sulfate. And halite comes out when you have sodium chloride coming out of solution. And so those are all chemical sedimentary rocks that form from this stuff coming out of solution. Not chunks, but chemically coming out of solution. Okay, it looks like that might be where we have to stop today. Let's see where we're going to start next time. Oh, some pretty pictures. So this will be our little review. As we look at the pretty pictures, we'll be reviewing some. They have a little blurb there on asbestos. I'll look at that. Ah, here we go. Yeah, we'll look at these pictures right here. That's where we'll start. We started there one other time in the course. All right. Do you need a little break? Are you ready to go on the test? Ready. Okay. Are y'all going to another room? Okay. I think that's what you wanted to do last time. Okay, let me end this.